Welcome to our deep dive into one of the most exciting frontiers of space exploration. Today we're exploring a question that could redefine how we think about interstellar travel. Will fusion revolutionize space travel? Space travel has always been limited by the technology we use, from the early days of chemical rockets to more recent innovations like electric propulsion. Each step forward has brought us closer to exploring the stars, but these technologies still have significant limitations. Enter fusion technology. Fusion, the process that powers the sun, promises a near-limitless, clean source of energy. If we can harness it effectively, it could change everything we know about space travel. Fusion works by fusing atomic nuclei together to release energy. This is fundamentally different from fission, which splits atoms apart. Fusion has the potential to provide far more energy than fission without the same level of radioactive waste. Currently, scientists around the world are racing to make fusion a reality. From massive projects like ITER in France to smaller innovative startups, the progress is steady but challenging. Achieving sustainable fusion requires overcoming significant scientific and engineering hurdles. So why is fusion such a game changer for space travel? The energy density of fusion fuel is millions of times greater than that of chemical fuel. This means a fusion-powered spacecraft could travel much farther and faster than those using current propulsion methods. Imagine a spaceship that doesn't need to carry vast amounts of fuel. Fusion propulsion could drastically reduce the weight of spacecraft, making missions more efficient and less expensive. This could open up the entire solar system, and possibly even other star systems, to exploration. Fusion propulsion isn't just about speed and distance, it's also about sustainability. The primary fuel for fusion, isotopes of hydrogen, is abundant and can be extracted from water. This makes fusion an environmentally friendly option compared to conventional fuels. The potential impact of fusion on space travel is immense. Crewed missions to Mars could become faster and safer. Deep space probes could reach farther into our galaxy, sending back data from places we've only dreamed of exploring. In this video, we'll explore the intricacies of fusion technology, its current state, and its potential to revolutionize space travel. We'll look at the scientific breakthroughs needed, the challenges ahead, and the exciting possibilities that fusion holds for the future of humanity in space. Fusion energy is a form of power generated by fusing two atomic nuclei to form a heavier nucleus. Unlike fission, which splits atoms apart, fusion brings them together. This process releases a tremendous amount of energy. It's the same reaction that powers the sun and other stars. By harnessing this power, we aim to create a nearly limitless, clean energy source. The potential of fusion energy lies in its fuel sources. It primarily uses isotopes of hydrogen, such as deuterium and tritium. These isotopes are abundant and can be extracted from water and lithium. This makes fusion a more sustainable option compared to fossil fuels. Additionally, fusion reactions produce far less radioactive waste than fission. One of the most significant advantages of fusion energy is its safety. Unlike nuclear fission reactors, fusion reactors don't pose a meltdown risk. If something goes wrong, the reaction simply stops. This inherent safety feature makes fusion an attractive option for future energy needs. Furthermore, the byproducts of fusion are generally non-toxic. Fusion energy also has the potential to provide a continuous power supply. Unlike solar or wind energy, which depend on weather conditions, fusion can operate continuously. This reliability makes it a promising candidate for replacing baseload power plants. Moreover, it could help stabilize grids that rely heavily on intermittent renewable sources. The science behind fusion energy is complex, involving high temperatures and pressures. Achieving the conditions necessary for fusion on Earth requires advanced technology. Researchers have developed devices like tokamaks and stellarators to contain and control the fusion reaction. These devices use powerful magnetic fields to confine the hot plasma where fusion occurs. Despite the challenges, significant progress has been made in fusion research. Experiments around the world have demonstrated the feasibility of achieving fusion conditions. Projects like ITER in France are working towards making fusion energy a practical reality. These collaborative efforts are crucial for overcoming the remaining technical barriers. Fusion energy research is also driving advancements in other fields. The technologies developed for fusion have applications in materials science, superconductivity, and more. These spin-offs benefit various industries, contributing to overall scientific and technological progress. Furthermore, the pursuit of fusion energy inspires the next generation of scientists and engineers. One of the critical challenges in fusion energy is achieving net energy gain. This means producing more energy from the fusion reaction than is used to initiate it. While this milestone has not yet been reached, experimental reactors have come close. Achieving net energy gain is a key goal for future fusion projects. In addition to technical challenges, fusion energy faces economic and political hurdles. The cost of developing and deploying fusion technology is high. Sustained investment and international cooperation are essential for progress. Policymakers must also support research and development efforts to ensure the realization of fusion energy. Public perception of fusion energy is another important factor. Educating people about the benefits and safety of fusion can help build support. Outreach and communication efforts are vital for addressing misconceptions and fostering enthusiasm. This support can drive funding and policy decisions that favor fusion development. The timeline for commercial fusion energy is still uncertain. While progress is being made, it may take several decades before fusion power plants become a reality. However, the long-term potential of fusion makes it worth pursuing. Continued investment and research are essential to overcoming the remaining obstacles. Environmental benefits are a significant advantage of fusion energy. It produces no greenhouse gas emissions during operation. This makes fusion a clean energy source that can help combat climate change. Additionally, the small amount of waste produced is less hazardous and easier to manage than fission waste. Fusion energy could play a crucial role in a diversified energy portfolio. By complementing other renewable sources, it can help ensure a stable and reliable energy supply. This diversification is key to building resilient energy systems. Fusion's potential to provide consistent baseload power makes it an invaluable addition. The international nature of fusion research fosters global cooperation. Scientists and engineers from different countries work together on projects like ITER. This collaboration enhances scientific understanding and promotes peace and stability. By working together towards a common goal, countries can strengthen their diplomatic ties. Ultimately, fusion energy represents a transformative step for humanity. Its potential to provide clean, abundant energy could revolutionize how we power our world. While challenges remain, the pursuit of fusion energy is a testament to human ingenuity and determination. The journey towards fusion power is as important as the destination. Fusion energy and fission energy are both forms of nuclear power, but they operate on different principles. Fission involves splitting heavy atomic nuclei, such as uranium or plutonium, into lighter nuclei. This process releases energy and is the basis for current nuclear power plants. Fusion, on the other hand, combines light nuclei, like those of hydrogen isotopes, to form heavier nuclei, releasing energy in the process. One of the key differences between fusion and fission is the fuel used. Fission relies on rare and finite resources like uranium, which require extensive mining and processing. Fusion uses isotopes of hydrogen, which are more abundant and can be extracted from water and lithium. This difference in fuel sources makes fusion a more sustainable long-term option. Safety is another major distinction. Fission reactors have the potential for catastrophic failures, such as meltdowns, which can release significant amounts of radioactive material. Fusion reactors, however, have no risk of meltdown. If a fusion reaction goes awry, it simply stops, making it inherently safer. Radioactive waste management is a critical issue in nuclear power. Fission generates a large amount of high-level radioactive waste that remains hazardous for thousands of years. Fusion produces much less radioactive waste, and the waste it does generate is typically less harmful and has a shorter half-life. This makes fusion a cleaner alternative in terms of waste management. The energy yield from fusion reactions is significantly higher than that from fission. Fusion reactions can release about 4 times more energy per unit mass of fuel compared to fission reactions. This higher energy density makes fusion an attractive option for meeting the growing global energy demands. Fission reactors are already in operation worldwide, providing a substantial portion of the world's electricity. Fusion reactors, however, are still in the experimental stage. Despite significant advancements, practical and commercially viable fusion power plants have yet to be realized. This difference in maturity between the two technologies impacts current energy policy and investment decisions. The environmental impact of fusion is considerably lower than that of fission. Fission power plants can impact the environment through mining, radioactive waste, and the risk of accidental releases. Fusion's primary environmental advantage is the lack of greenhouse gas emissions and minimal radioactive waste, making it a more environmentally friendly option. Economically, the initial costs for building fusion reactors are expected to be high. However, the operational costs could be lower in the long term due to the abundance of fuel and lower waste management costs. Fission reactors, while expensive to build, also face high costs related to safety measures, waste disposal, and decommissioning. Public perception of nuclear energy has been shaped largely by the risks associated with fission. Accidents like Chernobyl and Fukushima have left lasting impressions on the public consciousness. Fusion, with its safety advantages and cleaner waste profile, has the potential to change the narrative around nuclear power if it can be successfully developed and deployed. Fusion energy has the potential to complement existing renewable energy sources like solar and wind. While fission plants can provide stable baseload power, fusion could offer a similarly reliable but cleaner alternative. The integration of fusion power could enhance the stability and sustainability of the global energy grid. The geopolitical implications of fusion versus fission are also noteworthy. Countries with large reserves of uranium hold significant geopolitical power in the current energy landscape. Fusion, using more widely available materials, could democratize energy access and reduce geopolitical tensions related to energy resources. Research and development in fusion technology are driving innovations in various scientific fields. The challenges of containing and controlling fusion reactions have led to advancements in materials science, superconductivity, and plasma physics. These innovations have the potential to benefit other industries beyond energy production. Fusion's potential for providing nearly limitless energy aligns with global efforts to combat climate change. Reducing reliance on fossil fuels and cutting greenhouse gas emissions are crucial goals. Fusion energy, with its minimal environmental footprint, could play a key role in achieving a sustainable energy future. The workforce and skills required for fusion energy differ from those in fission. Fusion research demands expertise in advanced fields, such as plasma physics, engineering, and materials science. Developing these skills will require investment in education and training programs to prepare the next generation of scientists and engineers. In summary, while both fission and fusion offer pathways to nuclear energy, they differ significantly in terms of fuel sources, safety, waste management, and environmental impact. Fusion, still in development, holds the promise of a cleaner, safer, and more sustainable energy future compared to fission. Continued investment and research are essential to unlocking the full potential of fusion energy. Fusion energy production begins with the fusion of light atomic nuclei, typically isotopes of hydrogen like deuterium and tritium. These isotopes are heated to extremely high temperatures, creating a plasma state where the electrons are separated from the nuclei. In this state, the positively charged nuclei can overcome their natural repulsion and collide. To achieve the necessary conditions for fusion, the plasma must be heated to temperatures exceeding tens of millions of degrees. This is far hotter than the core of the Sun. At these temperatures, the kinetic energy of the particles is high enough to allow them to come close enough for the strong nuclear force to overcome the electrostatic repulsion between them. Containing such a hot plasma is a significant challenge. Traditional materials would melt under these conditions, so magnetic confinement is used. Devices called tokamaks and stellarators utilize powerful magnetic fields to confine and stabilize the plasma. These magnetic fields create a donut-shaped configuration that keeps the plasma away from the reactor walls. In a tokamak, the plasma is confined by a combination of magnetic fields produced by external coils and the current driven through the plasma itself. This configuration allows for the control and maintenance of the necessary conditions for fusion to occur. Tokamaks are currently the most researched and developed type of fusion reactors. Stellarators, on the other hand, use twisted magnetic fields generated by external coils alone, without relying on plasma current. This design aims to improve stability and reduce the challenges associated with maintaining the plasma current. Stellarators are more complex to construct, but offer potential advantages in continuous operation. Another approach to achieving fusion is inertial confinement, which involves using lasers or ion beams to compress a small pellet of fuel to extremely high densities and temperatures. The rapid compression generates the conditions necessary for fusion in a very short time. This method is being explored in facilities like the National Ignition Facility in the United States. In both magnetic and inertial confinement fusion, the goal is to achieve a state called ignition, where the fusion reactions become self-sustaining. This means the energy produced by the fusion reactions is enough to maintain the conditions for further fusion reactions without additional external energy input. When deuterium and tritium nuclei fuse, they form a helium nucleus and a high-energy neutron. The energy released in this reaction is primarily carried by the neutron, which escapes the plasma and can be captured in a surrounding blanket material. This blanket absorbs the neutron's energy and converts it into heat, which can then be used to generate electricity. The heat generated by the fusion reactions is used to produce steam, which drives turbines connected to electrical generators, much like conventional power plants. The efficiency of this conversion process is crucial for the overall feasibility of fusion power. The materials used in the reactor's construction must withstand the intense neutron bombardment and extreme temperatures. Advanced materials research is focused on developing alloys and composites that can endure these harsh conditions over extended periods. These materials are critical for the longevity and safety of fusion reactors. The process of fueling a fusion reactor involves injecting deuterium and tritium into the plasma. Maintaining the correct fuel ratio and ensuring continuous supply is essential for sustained fusion reactions. Researchers are developing sophisticated systems for fuel injection and management. Another aspect of fusion energy production is dealing with the helium ash produced by the reactions. The helium nuclei, also known as alpha particles, can accumulate in the plasma and dilute the fuel, reducing the efficiency of the reactions. Effective methods for removing this helium ash are necessary to maintain optimal plasma conditions. Fusion energy production also requires precise control over the plasma's shape and stability. Advanced diagnostic tools and real-time feedback systems are employed to monitor and adjust the plasma conditions continually. These technologies are vital for maintaining the delicate balance needed for sustained fusion. Research and development in fusion energy are highly collaborative, involving scientists and engineers from around the world. Large international projects like ITER bring together expertise and resources from multiple countries to overcome the technical challenges of fusion energy production. The progress made in fusion research has brought us closer to realizing its potential as a virtually limitless and clean energy source. As technology advances and experimental reactors achieve higher performance levels, the dream of harnessing fusion energy for practical use becomes increasingly attainable. Fusion energy offers several significant advantages over other energy sources, starting with its fuel abundance. Deuterium can be extracted from seawater, and tritium can be bred from lithium, both of which are plentiful. This contrasts sharply with fossil fuels, which are finite and depleting. Another key advantage is the minimal environmental impact. Fusion produces no greenhouse gases during operation, which means it doesn't contribute to climate change. This positions fusion as a crucial player in efforts to reduce global carbon emissions and combat global warming. Safety is a major benefit of fusion energy. Unlike fission reactors, fusion reactors have no risk of a runaway reaction. If any disturbance occurs, the reaction simply stops. This inherent safety reduces the risk of catastrophic failures and makes fusion power plants safer for communities. Fusion energy generates significantly less radioactive waste compared to fission. The waste products of fusion are primarily helium, a non-toxic inert gas, and some low-level radioactive materials with much shorter half-lives. This simplifies waste management and reduces long-term environmental hazards. The energy yield from fusion is extraordinarily high. A small amount of fusion fuel produces a massive amount of energy, much more than what is obtained from fossil fuels or fission. This high energy density means that fusion could vast amounts of energy from relatively small amounts of fuel. Fusion power plants have the potential to provide a continuous and stable supply of energy. Unlike solar and wind, which are intermittent and weather-dependent, fusion can operate continuously. This makes it an ideal candidate for baseload power generation, ensuring a reliable energy supply. Fusion energy also enhances energy security. By using widely available materials, fusion reduces dependency on geopolitical hotspots rich in fossil fuels. This can lead to more stable energy prices and a more secure energy supply globally. The operational safety of fusion reactors is another advantage. Fusion reactors do not require the high-pressure systems used in fission reactors, thereby reducing the risk of explosion. This operational simplicity translates to lower risks and potentially lower insurance and safety costs. The long-term sustainability of fusion energy is unmatched. With virtually limitless fuel supplies and minimal environmental impact, fusion can meet energy needs for thousands of years. This contrasts with the finite nature of fossil fuels and the environmental challenges they pose. Fusion energy can help reduce air pollution. Fossil fuel combustion releases harmful pollutants like sulfur dioxide and nitrogen oxides, contributing to smog and respiratory problems. Fusion produces no such pollutants, leading to cleaner air and improved public health. The economic benefits of fusion energy include job creation and technological advancement. Developing and maintaining fusion reactors will create high-tech jobs and stimulate advances in science and engineering. These benefits extend beyond the energy sector, contributing to broader economic growth. Fusion energy supports energy independence. By relying on abundant, locally available fuels, countries can reduce their reliance on imported energy. This fosters greater economic stability and reduces exposure to international energy market fluctuations. The adaptability of fusion technology offers further advantages. Fusion reactors can be integrated into existing power grids and infrastructure, facilitating the transition from fossil fuels. This flexibility allows for gradual and manageable shifts to cleaner energy sources. Fusion energy promotes international cooperation. Large-scale projects like ITER involve collaboration among many countries, fostering global scientific and technological exchange. This cooperation can lead to shared advancements and a more unified approach to addressing global energy challenges. Lastly, the pursuit of fusion energy drives innovation. The challenges of developing fusion technology spur advancements in materials science, superconductivity, and plasma physics. These innovations have the potential to benefit many other fields, amplifying the positive impact of fusion research. Fusion research has made significant strides over the past few decades, moving closer to achieving practical fusion energy. One of the most prominent projects in this field is the International Thermonuclear Experimental Reactor, or ITER. Located in France, ITER is a collaboration between 35 nations aiming to demonstrate the feasibility of fusion as a large-scale and carbon-free source of energy. ITER represents the largest and most ambitious fusion experiment to date. The project's goal is to produce 500 megawatts of fusion power from an input of 50 megawatts, achieving a 10-fold energy gain. Construction of ITER is well underway, with key components being assembled and installed, signaling significant progress toward its first plasma operations. In addition to ITER, other fusion research facilities are making notable advancements. The Joint European Torus, or JET, in the United Kingdom, has set records for the amount of energy produced in fusion experiments. JET serves as a testing ground for ITER, helping to refine techniques and technologies that will be used in the larger reactor. The United States is home to several prominent fusion research initiatives. The National Ignition Facility at Lawrence Livermore National Laboratory focuses on inertial confinement fusion, using powerful lasers to compress hydrogen fuel and initiate fusion reactions. Recent experiments have achieved important milestones, bringing the goal of ignition closer. In Asia, China's experimental advanced superconducting tokamak, or EAST, has achieved significant breakthroughs in maintaining high-temperature plasmas for extended periods. These achievements are crucial for developing stable and continuous fusion reactions, a key requirement for practical fusion power plants. Private sector investment in fusion research is also growing. Companies like Commonwealth Fusion Systems and TAE Technologies are developing innovative approaches to fusion energy. These firms aim to accelerate the timeline for achieving commercial fusion power, leveraging advances in materials science, superconductors, and artificial intelligence. Advancements in superconducting materials are pivotal for fusion research. Superconductors can carry much higher electrical currents without resistance, enabling stronger magnetic fields for plasma confinement. Recent progress in high-temperature superconductors promises to enhance the performance and reduce the costs of future fusion reactors. Diagnostics and control systems are also evolving rapidly. Cutting-edge technologies allow researchers to monitor and control plasma behavior with unprecedented precision. Real-time data analysis and machine learning algorithms help optimize fusion conditions, improving efficiency and stability in experimental reactors. Despite these advancements, challenges remain in achieving sustained and economically viable fusion energy. Key issues include managing the extreme conditions within reactors, such as intense heat and neutron flux, and developing materials that can withstand these conditions over long periods. Research into alternative fusion approaches is ongoing. Concepts like stellarators, field-reversed configurations, and magnetic mirrors offer different pathways to achieving fusion. These alternative designs may address some of the challenges faced by traditional tokamak and laser-based approaches. International collaboration is a cornerstone of fusion research. Projects like ITER benefit from the combined expertise and resources of multiple countries. This collaborative spirit extends to smaller projects and initiatives, fostering a global community dedicated to advancing fusion science and technology. Funding for fusion research remains a critical factor. Governments and private investors must continue to support fusion initiatives to sustain progress. Recent increases in funding reflect growing recognition of fusion's potential to address global energy needs and combat climate change. Public engagement and education are essential for the future of fusion research. Building public understanding and support can help secure the necessary funding and policy backing. Outreach efforts aim to inform and inspire, highlighting the transformative potential of fusion energy. As fusion research progresses, the goal of achieving net energy gain, where the energy output from fusion exceeds the input energy, remains a primary focus. Recent experimental successes provide optimism that this milestone will be reached, paving the way for the next generation of fusion reactors. Looking ahead, the transition from experimental reactors to commercial fusion power plants will require continued innovation and investment. The current trajectory of fusion research suggests that with sustained effort, fusion energy could become a practical and widespread energy source within the next few decades. Chemical propulsion is the most established method of propelling spacecraft. It relies on chemical reactions to produce thrust and has been the cornerstone of space exploration since the beginning. The basic principle involves combusting a fuel with an oxidizer to produce high-pressure and high-temperature gases. These gases are expelled through a nozzle to generate thrust, pushing the spacecraft forward. There are two main types of chemical propulsion: solid propellant and liquid propellant. Solid propellant rockets have a fixed mixture of fuel and oxidizer in a solid form, making them simple and reliable, but less controllable once ignited. Liquid propellant rockets use separate tanks for fuel and oxidizer, allowing for more control over the combustion process. These rockets can be throttled, shut down, and restarted, providing greater flexibility for various mission profiles. Bipropellant systems use two separate liquid components, a fuel and an oxidizer. The most common example is the combination of liquid hydrogen and liquid oxygen, which produces a high specific impulse and efficient thrust. Monopropellant systems use a single chemical that decomposes to produce thrust. An example is hydrazine, which, when passed over a catalyst, breaks down into hot gases that provide thrust. These systems are simpler but generally less efficient than bipropellant systems. Chemical propulsion has powered every major space mission, from the Apollo moon landings to the Mars rovers. Its reliability and high thrust-to-weight ratio make it ideal for launching payloads from Earth's surface and performing rapid maneuvers in space. However, chemical propulsion has significant limitations. The energy density of chemical fuels is relatively low, meaning large amounts of fuel are required for missions, which adds weight and complexity. This limitation becomes more pronounced for long-duration missions beyond Earth orbit. The vast distances involved in interplanetary travel require propulsion systems with higher efficiency and lower fuel consumption than chemical propulsion can provide. Additionally, the need to carry both fuel and oxidizer limits the payload capacity of spacecraft. Every kilogram of fuel reduces the amount of scientific instruments, crew supplies, or other mission-critical equipment that can be carried. Despite these limitations, advances in chemical propulsion continue. Hybrid rocket engines, which combine elements of both solid and liquid propulsion, are being developed to offer improved performance and flexibility. High-energy propellants, such as those using exotic chemical compounds, are also being researched to increase the efficiency and thrust of chemical rockets. These advancements aim to push the boundaries of what is possible with chemical propulsion. Another area of innovation is in the design of more efficient and lightweight rocket engines. Advanced materials and manufacturing techniques are being used to create engines that are both more powerful and more reliable. Chemical propulsion will likely remain a vital part of space exploration for the foreseeable future. Its ability to deliver high thrust quickly is unmatched by other propulsion methods currently available. For launching payloads from Earth and performing critical maneuvers in space, chemical propulsion provides the necessary power and reliability. However, for missions that require long-duration travel, alternative propulsion methods will need to be developed. As we look to the future of space exploration, understanding the strengths and limitations of chemical propulsion will help guide the development of new technologies that can take us farther than ever before. Electric propulsion represents a significant advancement in space travel technology, offering higher efficiency compared to traditional chemical propulsion. It uses electrical energy to accelerate propellant to much higher speeds, resulting in greater fuel efficiency. The most common type of electric propulsion is ion thrusters. These devices ionize a propellant, usually xenon, and use electric fields to accelerate the ions to produce thrust. Ion thrusters are known for their high specific impulse, meaning they use fuel much more efficiently. Another type of electric propulsion is Hall effect thrusters. These thrusters use a magnetic field to trap electrons, creating an electric field that accelerates the ions. Hall thrusters are widely used on many satellites and spacecraft due to their balance of efficiency and thrust. Electric propulsion systems typically require a power source, such as solar panels or nuclear reactors, to generate the electricity needed to ionize and accelerate the propellant. This reliance on electrical power is a key difference from chemical propulsion systems. The efficiency of electric propulsion is particularly beneficial for long-duration missions. Spacecraft can carry less propellant and still achieve the necessary delta V, or change in velocity, for their missions. This makes electric propulsion ideal for deep space exploration.
One major advantage of electric propulsion is its ability to operate continuously over long periods. Unlike chemical rockets, which provide a short burst of high thrust, electric thrusters provide low thrust over extended durations, allowing for gradual but significant changes in velocity.
Electric propulsion has been successfully used in various missions. The Dawn spacecraft, for example, used ion propulsion to travel to and orbit the asteroid Vesta and the dwarf planet Ceres. Its mission would have been impossible with chemical propulsion alone. The technology is also used in satellite station keeping, where small adjustments are needed to maintain a satellite's orbit. Electric thrusters are perfect for this task due to their high efficiency and low fuel consumption. Despite its advantages, electric propulsion has limitations. The low thrust levels mean it is not suitable for launching payloads from Earth's surface, where high thrust is needed to overcome gravity. Instead, it is best used once the spacecraft is already in space. The reliance on a power source can also be a limitation. Solar panels work well in the inner solar system, but become less effective farther from the sun. Nuclear power sources can provide the necessary energy, but come with their own set of challenges and risks. Developments in electric propulsion are ongoing. Researchers are exploring advanced ion thruster designs, new propellant options, and ways to increase the power available to electric propulsion systems. These advancements aim to improve performance and expand the range of missions that can benefit from this technology. Electric propulsion could play a crucial role in future human missions to Mars and beyond. Its efficiency makes it possible to reduce the amount of fuel needed, which is a significant advantage for long-duration crewed missions where every kilogram counts. The technology also holds promise for asteroid mining and other commercial space ventures. Efficient propulsion systems could enable economically viable missions to extract resources from asteroids and transport them back to Earth or to other locations in space. As space agencies and private companies plan more ambitious missions, electric propulsion will likely become an essential part of the propulsion toolkit. Its ability to provide efficient, long-duration thrust opens up new possibilities for exploration and commercial activities in space. Understanding the capabilities and limitations of electric propulsion is crucial for designing the next generation of spacecraft. This technology, alongside others, will help humanity extend its reach into the solar system and beyond, pushing the boundaries of what is possible in space exploration. Nuclear fission propulsion is a powerful alternative to chemical and electric propulsion, utilizing the energy released from splitting heavy atomic nuclei. This method offers significantly higher energy density compared to chemical propulsion. One of the earliest concepts for nuclear fission propulsion was the nuclear thermal rocket, or NTR. In an NTR, a nuclear reactor heats a propellant, typically hydrogen, which then expands and is expelled to produce thrust. This method provides a much higher specific impulse than chemical rockets. The high efficiency of NTRs makes them attractive for deep space missions. They can reduce travel time to distant planets, which is crucial for crewed missions, where minimizing time in space is important for astronaut health. The Rover and Nerva programs in the United States during the 1950s and 1960s demonstrated the feasibility of nuclear thermal propulsion. These programs developed and tested several reactors, proving that the technology could work in principle. Nuclear fission propulsion is not limited to thermal rockets. Another concept is the nuclear electric propulsion system, which uses a nuclear reactor to generate electricity. This electricity then powers electric thrusters, combining the high energy density of nuclear power with the efficiency of electric propulsion. Despite its advantages, nuclear fission propulsion faces significant challenges. Safety concerns are paramount, both for the launch phase and in the event of a reactor failure. The potential release of radioactive materials poses a risk that must be carefully managed. Regulatory and political hurdles also exist. The use of nuclear reactors in space requires stringent oversight and international cooperation to ensure that all safety and environmental concerns are addressed. Radiation shielding is another critical issue. The reactor and other components must be adequately shielded to protect both the spacecraft's electronics and its crew from harmful radiation. Heat management is a significant engineering challenge as well. The reactor generates a substantial amount of heat, which must be dissipated to prevent the spacecraft from overheating. Advanced cooling systems are necessary to manage this heat effectively. Developments in materials science are crucial for advancing nuclear fission propulsion. High-temperature materials are needed to build reactors that can operate efficiently in the harsh environment of space. Testing and validation of nuclear propulsion systems pose unique challenges. Ground testing can simulate many conditions, but the full operational environment of space is difficult to replicate. In-space testing is often necessary to fully validate the technology. Public perception and acceptance of nuclear technology in space also play a role. Educating the public about the safety measures and benefits of nuclear propulsion is essential for gaining support for these technologies. Nuclear fission propulsion offers the potential for faster travel times to Mars and other distant destinations, which is a key advantage for future crewed missions. Shorter travel times reduce the exposure of astronauts to space radiation and the psychological challenges of long-duration missions. The potential for extended missions and deeper space exploration is greatly enhanced by nuclear fission propulsion. Missions to the outer planets and their moons, as well as crewed missions to Mars, become more feasible with this technology. As space exploration goals become more ambitious, the need for advanced propulsion systems like nuclear fission becomes more apparent. These systems offer the power and efficiency needed to take the next big steps in human space exploration. While current space propulsion technologies have enabled significant achievements, they also come with a range of limitations that restrict their potential. Understanding these limitations is crucial as we look toward more advanced systems like fusion propulsion. Chemical propulsion, despite its reliability and high thrust, is inherently inefficient for long-duration missions. The large amounts of fuel required add significant weight to spacecraft, limiting the payload capacity and increasing launch costs. The energy density of chemical fuels is relatively low, meaning that, for missions beyond Earth orbit, an impractical amount of fuel would be needed. This makes chemical propulsion less viable for deep space exploration. Electric propulsion, though highly efficient, produces low thrust. This makes it unsuitable for launching spacecraft from Earth or for missions that require quick acceleration. The long-duration, low-thrust nature of electric propulsion is a double-edged sword. The reliance on solar power for electric propulsion also limits its effectiveness. Solar panels become less efficient as the spacecraft travels farther from the Sun, reducing the power available for propulsion and other systems. Nuclear fission propulsion offers higher energy density, but it comes with significant safety concerns. The risks associated with launching a nuclear reactor into space and managing radiation pose substantial challenges. Regulatory hurdles and public perception issues further complicate the deployment of nuclear fission propulsion systems. Ensuring safety and gaining public support are critical yet challenging aspects of utilizing this technology. The complexity of nuclear fission systems also means they are more expensive and difficult to develop and test compared to chemical or electric propulsion. The need for advanced materials and cooling systems adds to the engineering challenges. Another limitation of current technologies is their dependence on Earth-based resources. Chemical fuels, solar panels, and even nuclear materials need to be launched from Earth, which adds to mission costs and complexity. Spacecraft using current propulsion methods are also limited in their ability to perform significant course corrections or adjustments once they are en route. The limited fuel capacity restricts maneuverability, which can be a critical factor for long-duration missions. Current propulsion systems are also less suitable for sustained human presence in space. The inefficiency and limitations in speed and payload capacity make it difficult to transport the necessary supplies and equipment for long-term missions. Interstellar travel remains a distant dream with current technologies. The vast distances and the need for sustained propulsion over long periods highlight the inadequacies of chemical, electric, and nuclear fission propulsion for such missions. The environmental impact of chemical propulsion is another concern. The production and use of rocket fuels contribute to pollution and carbon emissions, which are increasingly important considerations for space missions. The technical and logistical challenges of maintaining and refueling spacecraft with current technologies also pose significant hurdles. Long-term missions require reliable and sustainable propulsion systems, which current technologies struggle to provide. Finally, the economic costs associated with current propulsion technologies are substantial. High development, launch, and operational costs limit the frequency and scope of space missions, hindering our ability to explore more extensively. Addressing these limitations is essential for advancing space exploration. While current technologies have brought us far, overcoming their drawbacks will pave the way for more ambitious missions and ultimately a deeper understanding of our universe. The International Space Station is a prime example of an ongoing space mission relying on chemical propulsion for resupply missions. SpaceX's Dragon and Northrop Grumman's Cygnus spacecraft regularly deliver supplies using traditional rocket technology. NASA's Artemis program aims to return humans to the Moon and establish a sustainable presence. The Space Launch System and Orion spacecraft, both utilizing chemical propulsion, are central to these missions. The Mars Perseverance rover, launched in 2020, used the Atlas V rocket, a chemical propulsion system, to reach the Red Planet. Its mission is to search for signs of ancient life and collect samples for future return to Earth. The James Webb Space Telescope, set to revolutionize our understanding of the universe, was launched by an Ariane 5 rocket. This chemical propulsion system provided the necessary thrust to position the telescope at the second Lagrange point. The Parker Solar Probe, launched to study the Sun's outer atmosphere, relies on chemical propulsion for its initial journey and adjustments. Its findings are crucial for understanding solar winds and space weather. The Juno spacecraft, currently studying Jupiter, used a chemical rocket to leave Earth and an electric propulsion system for its deep space maneuvers. Juno's mission provides insights into Jupiter's atmosphere and magnetic field. ESA's Bepi-Colombo mission to Mercury combines chemical propulsion for launch with electric propulsion for its journey through the inner solar system. This dual approach maximizes efficiency and mission duration. The Voyager probes, launched in the late 1970s, used chemical propulsion to leave Earth and gravity assists for their journeys. They continue to send data from interstellar space, far beyond the capabilities of modern missions. The Hubble Space Telescope, launched by the Space Shuttle Discovery, used chemical propulsion to reach its orbit. Hubble has provided some of the most detailed images of distant galaxies and nebulae. The New Horizons mission to Pluto and beyond used the Atlas V rocket for its journey. After a flyby of Pluto, it continues to explore the Kuiper Belt, sending back valuable data about these distant objects. The Mars InSight lander, studying the interior of Mars, used a chemical rocket for its launch. Its findings help scientists understand the geological activity and structure of Mars. China's Tianwen-1 mission to Mars, which includes an orbiter, lander and rover, relies on chemical propulsion. This ambitious mission marks a significant step in China's space exploration efforts. India's Chandrayaan-2 mission, aimed at studying the Moon, used the GSLV Mk3 rocket. Despite challenges with its lander, the orbiter continues to provide valuable lunar data. The OSIRIS-REx mission, tasked with collecting samples from the asteroid Bennu, used the Atlas V rocket for launch. It will return these samples to Earth, offering insights into the early solar system. The upcoming Europa Clipper mission will use a chemical rocket to reach Jupiter's moon Europa. Its goal is to investigate the moon's potential habitability, focusing on its subsurface ocean. These missions illustrate the diverse applications and ongoing reliance on current propulsion technologies. They highlight the achievements and limitations of chemical and electric propulsion in modern space exploration. Fusion propulsion represents a revolutionary leap in space travel technology. Unlike chemical and fission propulsion, fusion relies on merging atomic nuclei to release vast amounts of energy. The basic idea behind fusion propulsion is to harness the power of the sun. By fusing isotopes of hydrogen, such as deuterium and tritium, a spacecraft could achieve unprecedented speeds and efficiency. Fusion propulsion systems would use a fusion reactor to produce high-energy plasma. This plasma would then be directed out of the spacecraft to create thrust, propelling the spacecraft forward. One of the main advantages of fusion propulsion is its high specific impulse. This means that a fusion engine can produce much more thrust per unit of fuel compared to chemical rockets. The fuel for fusion propulsion is also abundant. Deuterium can be extracted from seawater, and tritium can be bred from lithium, making it a nearly limitless resource for space travel. Another significant benefit is the relatively low production of radioactive waste. Fusion reactions primarily produce helium, an inert gas, which is much safer than the byproducts of fission reactions. The high energy density of fusion fuel allows for longer missions with less fuel. This makes it ideal for deep space exploration, where carrying large amounts of chemical fuel would be impractical. Fusion propulsion could drastically reduce travel times to distant planets and potentially enable interstellar missions. The increased speed would also reduce the time astronauts spend in the hazardous environment of space. Another approach is inertial confinement fusion, where fuel pellets are rapidly compressed and heated using lasers or ion beams to achieve the conditions necessary for fusion. Achieving and maintaining the high temperatures and pressures required for fusion is a major technical challenge. However, advancements in materials science and magnetic confinement technology are bringing this closer to reality. The concept of direct drive fusion propulsion involves using the energy from fusion reactions directly to accelerate propellant. This could potentially simplify the engine design and increase efficiency. The development of fusion propulsion systems requires significant investment and international collaboration. The complexities involved mean that it is a long-term goal, but the potential benefits make it a highly attractive pursuit. Fusion propulsion could also provide continuous thrust over long periods, unlike the short bursts of chemical rockets. This constant acceleration would allow spacecraft to reach higher velocities over time. Exploring the potential of fusion propulsion is a key step in advancing our capabilities for space exploration. As research progresses, it could unlock new possibilities for human and robotic missions far beyond our current reach. One potential design for fusion engines is the tokamak-based propulsion system. Tokamaks use magnetic confinement to control hot plasma, creating the necessary conditions for nuclear fusion. This design is one of the most researched due to its promising results in experimental reactors like ITER. The Stellarator is another design that utilizes twisted magnetic fields to confine plasma. Although less common than tokamaks, stellarators offer the advantage of potentially more stable plasma confinement, which could be beneficial for long-duration space missions. Direct fusion drive, or DFD, is a concept that integrates a fusion reactor with a magnetic nozzle to produce thrust. Developed by Princeton Plasma Physics Laboratory, DFD aims to provide both propulsion and electrical power for spacecraft, making it a versatile solution for deep space missions. The Polywell fusion reactor is a unique design that uses a combination of magnetic and electrostatic fields to confine plasma. This approach aims to achieve fusion conditions with potentially simpler and more compact machinery, suitable for space applications. Inertial confinement. Fusion, or ICF, involves compressing fuel pellets with lasers, or ion beams, to achieve the necessary temperatures and pressures for fusion. This method, though technologically challenging, could provide a powerful thrust if scaled up for space propulsion. Fusion-driven rockets are designed to use fusion reactions directly to heat propellant. The propellant, typically hydrogen, is then expelled to generate thrust. This approach leverages the high-energy output of fusion to achieve significant acceleration. The magnetic target fusion concept combines magnetic confinement with inertial compression. It uses magnetic fields to confine plasma while compressing it with liners or projectiles to trigger fusion reactions. This hybrid approach aims to harness the strengths of both confinement methods. Field reversed configuration, or FRC, involves creating a rotating magnetic field to confine plasma in a compact, cylindrical configuration. FRC designs are being explored for their potential to provide efficient, high-thrust propulsion with relatively simple machinery. Plasma jet magnetic nozzle engines use fusion to generate a high-velocity plasma jet. Magnetic nozzles then direct and accelerate this plasma to produce thrust. This design aims to combine the high efficiency of electric propulsion with the power of fusion. Fusion antimatter hybrid engines propose using antimatter to catalyze fusion reactions. The concept is based on the idea that antimatter could initiate fusion at lower temperatures and pressures, potentially simplifying reactor designs and improving efficiency. Pulsed fusion propulsion involves using a series of small, controlled fusion explosions to provide thrust. Each pulse generates a burst of energy that is directed out of the spacecraft, creating a propulsion system that can be precisely controlled for long-duration missions. The VISTA fusion propulsion system is a conceptual design that uses inertial confinement fusion to produce thrust. VISTA, which stands for Vehicle for Interplanetary Space Transport Application, aims to achieve high-speed travel for crewed missions to Mars and beyond. Helicon double-layer thrusters are being studied for their potential to use fusion-generated plasma. These thrusters create a double layer of plasma, accelerating ions to produce thrust. The addition of fusion could significantly boost their performance. Magneto-inertial fusion engines focus on compressing plasma with magnetic fields to trigger fusion. This design seeks to combine the efficiency of magnetic confinement with the high energy output of inertial compression, creating a powerful propulsion system. Finally, the antiproton catalyzed microfusion concept explores using antiprotons to trigger microfusion reactions within small fuel pellets. This approach could offer a compact and efficient way to achieve fusion propulsion, suitable for a wide range of space missions. These potential designs for fusion engines highlight the diversity of approaches being explored to harness fusion energy for space travel. Each design comes with its unique challenges and advantages, contributing to the ongoing quest for advanced propulsion technologies. Fusion propulsion offers several significant advantages over traditional chemical propulsion, starting with its remarkable efficiency. The specific impulse of fusion propulsion is much higher, meaning it can produce more thrust per unit of fuel compared to chemical rockets. The fuel for fusion propulsion is abundant and accessible. Deuterium, one of the primary fuels, can be extracted from seawater, while tritium can be bred from lithium. This abundance contrasts sharply with the limited availability of chemical rocket fuels. Fusion propulsion produces minimal environmental impact. The primary byproduct of fusion reactions is helium, an inert gas that poses no environmental hazards, unlike the toxic byproducts of chemical propulsion. The energy density of fusion fuel is millions of times greater than that of chemical fuels. This high energy density means that spacecraft can carry less fuel for longer missions, significantly reducing launch mass and increasing payload capacity. The ability to generate continuous thrust is another key advantage. Unlike chemical rockets, which provide short bursts of high thrust, fusion propulsion can maintain steady acceleration over extended periods, enabling faster travel times to distant destinations. Fusion propulsion could enable more ambitious missions, such as manned missions to Mars, or even interstellar travel. The higher speeds achievable with fusion engines reduce travel time, which is crucial for long-duration missions and crewed space exploration. Safety is also a major advantage. Fusion reactors do not pose the same risks of catastrophic failure as chemical rockets. There is no risk of a large-scale explosion, and the absence of highly toxic chemicals reduces the potential for environmental contamination. The flexibility of fusion propulsion allows for more complex mission profiles. Spacecraft can perform significant course adjustments and maneuvers without the need for large amounts of chemical fuel, providing greater operational versatility. Fusion propulsion supports sustainable space exploration. The abundant and clean fuel sources, coupled with the high efficiency of fusion engines, make it a more sustainable option for long-term human presence in space. The reduced need for refueling infrastructure is another benefit. Fusion-powered spacecraft would not require the extensive fuel supply chains needed for chemical rockets, simplifying mission logistics and reducing costs. The potential for dual-use technology is significant. Fusion reactors can provide both propulsion and electrical power for spacecraft, supporting a wide range of scientific instruments, life support systems, and other mission-critical technologies. The development of fusion propulsion could drive advancements in related technologies. Innovations in materials science, plasma physics, and reactor design could have broader applications beyond space travel, benefiting multiple industries. Fusion propulsion aligns with global sustainability goals. Its development supports efforts to reduce reliance on fossil fuels and minimize environmental impact, contributing to a cleaner and more sustainable future. The capability for rapid transit between Earth and other celestial bodies opens up new possibilities for space colonization and resource utilization. Shorter travel times make it feasible to establish permanent human settlements on the Moon, Mars, and beyond. Fusion propulsion represents a transformative technology that could revolutionize space travel. Its numerous advantages over chemical propulsion make it a promising candidate for the future of space exploration, enabling humanity to reach farther and achieve more in our quest to explore the cosmos. Fusion propulsion and nuclear fission propulsion both utilize nuclear reactions, but they operate on fundamentally different principles and offer distinct advantages and challenges. Understanding these differences is crucial for evaluating their potential for space travel. Fusion propulsion relies on combining light atomic nuclei to release energy, while fission propulsion splits heavy atomic nuclei. This fundamental difference leads to variations in fuel requirements, energy output, and safety profiles. The fuel for fusion, primarily deuterium and tritium, is more abundant and easier to obtain than the enriched uranium or plutonium used in fission reactors. This makes fusion a more sustainable and potentially cheaper option in the long run. Fusion reactions produce minimal radioactive waste, primarily helium, an inert and non-toxic gas. In contrast, fission reactions generate significant amounts of long-lived radioactive waste, posing long-term disposal and environmental challenges. Safety is a major advantage of fusion propulsion. Fusion reactors do not carry the same risk of catastrophic meltdown as fission reactors. The reaction can be quickly halted by stopping the fuel supply, minimizing the risk of a major accident. Fusion propulsion systems are inherently more stable. They require extreme conditions to maintain the reaction, so any disruption quickly cools the plasma and stops the fusion process. Fission reactors, on the other hand, can continue to generate heat even after the reaction is stopped. The energy density of fusion fuel is significantly higher than that of fission fuel, allowing for greater thrust and efficiency. This higher energy density can translate to faster travel times and the ability to carry larger payloads on deep space missions. Fusion propulsion systems can provide continuous thrust over long durations, which is ideal for deep space exploration. Fission propulsion systems typically provide high thrust for shorter periods, making them less suited for long-duration missions. While both propulsion methods offer high specific impulse compared to chemical rockets, fusion's higher efficiency and lower fuel mass requirements give it a distinct advantage in long-term sustainability and mission planning. The complexity and technical challenges of achieving controlled fusion are significant, involving advanced materials and precise plasma confinement. Fission propulsion, while technologically mature, faces challenges related to radiation shielding and thermal management. The development and testing of fusion propulsion systems are still in the experimental stage, requiring significant investment and international collaboration. Fission propulsion technology, though advanced, still faces public and regulatory scrutiny due to safety concerns. Public perception of nuclear technology is generally more favorable towards fusion due to its safer and cleaner profile. Fission, associated with nuclear accidents and radioactive waste, often encounters greater resistance and regulatory hurdles. The dual-use potential of fusion propulsion is notable. Fusion reactors can provide not only propulsion, but also electrical power for spacecraft systems, supporting a wide range of mission requirements. Fission reactors, while capable of similar applications, are more complex and costly to implement. Fusion propulsion aligns more closely with long-term goals for sustainable and environmentally friendly space exploration. Its minimal waste and abundant fuel sources make it an attractive option for future missions. Comparing fusion and fission propulsion highlights the transformative potential of fusion technology. While both offer significant advancements over chemical propulsion, fusion's safety, efficiency, and sustainability give it a promising edge for the future of space travel. The development timeline for fusion propulsion is ambitious and complex, driven by advancements in science and engineering. Currently, most fusion propulsion concepts are in the theoretical or early experimental stages, with significant research and development required before they become viable for space missions. In the next decade, we expect to see substantial progress in plasma confinement techniques and materials science. These advancements will help achieve the necessary conditions for sustained fusion reactions, moving us closer to practical fusion propulsion systems. By the 2030s, prototype fusion propulsion systems could begin to emerge. These prototypes will likely be tested in ground-based facilities to validate their performance and identify areas for improvement. This decade will be crucial for demonstrating the feasibility of fusion propulsion. Concurrent with these developments, international collaboration and funding will be essential. Projects like ITER and various private sector initiatives will contribute valuable knowledge and resources, accelerating the pace of innovation. In the 2040s, we may see the first in-space tests of fusion propulsion systems. These initial tests will focus on validating the technology in the space environment, assessing its performance, and identifying any unforeseen challenges. Successful in-space tests will pave the way for more ambitious missions. By the mid-2040s, fusion propulsion could be used for robotic missions to distant destinations, demonstrating its capability to significantly reduce travel times compared to chemical propulsion. Human missions could follow in the late 2040s or early 2050s. These missions might include crewed expeditions to Mars or even more distant targets, leveraging the high efficiency and sustained thrust of fusion propulsion to ensure shorter and safer journeys. Throughout this period, continuous advancements in reactor design, fuel handling, and heat management will be critical. Each technological breakthrough will bring fusion propulsion closer to becoming a reliable option for deep space exploration. The development timeline will also depend on regulatory and safety milestones. Establishing international standards and protocols for the use of fusion propulsion in space will be necessary to ensure safe and sustainable practices, and economic factors will play a significant role in the timeline. The cost of developing and deploying fusion propulsion systems must be competitive with existing technologies to justify the investment and transition. Public and political support will influence funding and regulatory environments. As awareness of the benefits of fusion propulsion grows, it could drive increased investment and expedited regulatory processes. Educational initiatives and workforce development will be essential to support the growing fusion industry. Training the next generation of scientists, engineers, and technicians will ensure a skilled workforce capable of advancing this complex technology. Collaborative efforts between government space agencies, private companies, and international partners will be crucial for sharing knowledge and resources. These partnerships will help overcome technical and financial barriers more efficiently. As we move into the latter half of the century, fusion propulsion could become the standard for deep space missions. The continuous improvement of technology and reduction in costs will make it a practical choice for a wide range of space exploration endeavors. Ultimately, the timeline for the development of fusion propulsion is driven by both technological advancements and strategic collaborations. The journey is challenging, but the potential rewards make it one of the most exciting frontiers in space exploration. The energy output of fusion reactions is extraordinary, offering a potential power source far exceeding that of chemical or even fission reactions. This immense energy comes from the fusion of light atomic nuclei, typically isotopes of hydrogen. When deuterium and tritium nuclei combine, they form a helium nucleus and a high-energy neutron. This reaction releases a significant amount of energy due to the mass difference between the reactants and the products, as described by Einstein's equation, E mc2. The energy released per fusion reaction is much higher than that of fission. For instance, a single deuterium-tritium fusion event releases about 17.6 MeV of energy, which is orders of magnitude greater than typical chemical reactions. In practical terms, a small amount of fusion fuel can produce an enormous amount of energy. 1 gram of deuterium-tritium fuel can release the same amount of energy as burning thousands of liters of gasoline, highlighting the efficiency of fusion. This high energy density means that spacecraft equipped with fusion propulsion would require much less fuel for long missions, drastically reducing launch weights and allowing for more payload capacity. Fusion reactions primarily produce high-energy neutrons which can be captured and converted into heat. This heat can then be used to generate electricity or directly propel a spacecraft through various propulsion systems. The challenge lies in achieving and sustaining the conditions necessary for these reactions. Fusion requires extremely high temperatures, on the order of millions of degrees, to overcome the electrostatic repulsion between positively charged nuclei. Magnetic confinement fusion aims to contain this hot plasma using powerful magnetic fields. Devices like tokamaks and stellarators are designed to maintain the necessary conditions for sustained fusion reactions over long periods. Inertial confinement fusion, on the other hand, uses intense laser or ion beams to compress fuel pellets to achieve the required temperature and pressure. This method focuses on creating short, intense bursts of fusion energy. The potential energy output of fusion reactions can support continuous thrust for space missions. Unlike the short bursts of chemical propulsion, fusion engines can provide steady acceleration, enabling faster travel to distant destinations. Fusion energy is also remarkably clean. The primary byproduct, helium, is non-toxic and non-radioactive. This makes fusion an environmentally friendly power source, both for space missions and potential terrestrial applications. The high-energy neutrons produced in fusion reactions can be challenging to manage. They require effective shielding to protect spacecraft and crew. But advancements in materials science are addressing these challenges. The energy output from fusion reactions can be harnessed in different ways, depending on the propulsion system. For instance, direct conversion systems aim to transform fusion energy directly into kinetic energy, enhancing propulsion efficiency. Thermal conversion systems, which use heat exchangers, can also be highly effective. The heat from fusion reactions can generate steam to drive turbines or directly heat propellant for thrust. The immense energy output of fusion reactions represents a transformative potential for space travel. By unlocking the power of fusion, humanity can embark on more ambitious missions, exploring deeper into our solar system and beyond with unprecedented speed and efficiency. Fuel sources for fusion propulsion primarily involve isotopes of hydrogen, specifically deuterium and tritium. These isotopes are chosen for their favorable fusion properties, which allow them to release significant amounts of energy when combined. Deuterium, a stable isotope of hydrogen, has 1 proton and 1 neutron in its nucleus. It is naturally occurring and can be extracted from seawater. The abundance of deuterium makes it an attractive fuel source for fusion reactors. Tritium, another isotope of hydrogen, contains 1 proton and 2 neutrons. Unlike deuterium, tritium is radioactive and has a half-life of about 12 years. Tritium is not found in large quantities in nature and must be produced, typically by irradiating lithium. The combination of deuterium and tritium is currently the most efficient fuel mix for achieving fusion. When these isotopes fuse, they produce a helium nucleus, a neutron, and a large amount of energy, making this reaction highly desirable for fusion propulsion. Extracting deuterium from seawater involves relatively straightforward chemical processes. Given the vast amount of seawater on Earth, the supply of deuterium is virtually limitless, ensuring a sustainable fuel source for future fusion reactors. Producing tritium involves neutron activation of lithium. In a fusion reactor, lithium can be used to breed tritium by capturing neutrons released during the fusion process. This breeding cycle helps sustain the fuel supply, making tritium production feasible. Lithium itself is an abundant element, found in the Earth's crust and seawater. The process of breeding tritium from lithium not only provides the necessary fuel, but also integrates well with the design of fusion reactors, especially those that use lithium-based materials in their construction. An alternative fusion fuel cycle involves deuterium and helium-3. Helium-3 is a rare isotope of helium with 2 protons and 1 neutron. Fusion reactions involving helium-3 produce less neutron radiation, which is beneficial for reducing shielding requirements and extending the life of reactor components. Helium-3 is scarce on Earth, but is believed to be more abundant on the Moon and other celestial bodies. This potential availability has sparked interest in mining helium-3 as a future fusion fuel, which could play a role in lunar and space exploration missions. Advanced research is exploring other fuel cycles, such as deuterium-deuterium fusion, which uses only deuterium. While the energy output and reaction conditions differ from deuterium-tritium fusion, these alternatives offer the possibility of reducing reliance on tritium. The choice of fusion fuel affects reactor design, operational conditions, and safety measures. Deuterium-tritium fusion, with its high energy output, remains the primary focus, but ongoing research into alternative fuels aims to optimize performance and sustainability. The efficient handling and storage of fusion fuels are crucial for mission planning. Deuterium, as a stable isotope, is relatively easy to store, while tritium requires careful management due to its radioactivity and limited half-life. The development of robust fuel supply chains and breeding cycles is essential for the practical implementation of fusion propulsion. Advances in materials science, fuel processing, and reactor technology will all contribute to making fusion fuels more accessible and reliable. The potential of fusion fuels, particularly the abundant deuterium and the sustainably produced tritium, offers a promising path forward for long-term, high-efficiency space exploration. By harnessing these fuels, we can unlock new possibilities for traveling deeper into the cosmos. The environmental impact of fusion propulsion is considerably less harmful compared to traditional propulsion methods, making it an attractive option for future space travel. One of the primary benefits is the minimal production of long-lived radioactive waste. Fusion reactions, particularly those involving deuterium and tritium, produce helium as a byproduct. Helium is an inert gas and poses no environmental threat, unlike the toxic byproducts from chemical rockets or the radioactive waste from nuclear fission. The high energy density of fusion fuel means that spacecraft can carry less fuel for longer missions. This reduction in fuel mass translates to fewer launches, and consequently, a lower environmental footprint associated with space missions. During launch, chemical rockets release significant amounts of carbon dioxide and other pollutants into the atmosphere. Fusion propulsion, by contrast, does not rely on combustion, thereby eliminating these emissions and reducing the impact on Earth's atmosphere. Fusion propulsion systems are designed to operate in space, meaning they do not contribute to atmospheric pollution once they leave Earth. The clean nature of fusion reactions ensures that spacecraft powered by fusion do not release harmful substances into space. The use of abundant fuels like deuterium, extracted from seawater, and tritium, bred from lithium, means that fusion propulsion does not deplete Earth's natural resources. This sustainability is a key advantage over fossil fuels and other limited resources. Managing tritium, a radioactive isotope, requires careful handling to prevent environmental contamination. However, modern containment methods and the relatively short half-life of tritium make it manageable compared to the long-lived waste from fission reactors. The infrastructure required for fusion propulsion, including reactors and fuel processing facilities, has a relatively small environmental footprint. Advances in technology, are continually reducing the energy and material costs of these facilities. Fusion propulsion's potential to enable faster travel reduces the duration of missions, which can decrease the cumulative environmental impact of long-term space operations. Shorter missions mean less reliance on extensive support systems that constrain resources. In the context of planetary exploration, fusion propulsion could minimize the need for in-situ resource utilization, which involves extracting and using resources from other celestial bodies. This reduction in resource extraction helps preserve the integrity of these environments. The development of fusion propulsion can drive advancements in related green technologies. Innovations in materials, energy production, and waste management for fusion reactors have potential applications on Earth, contributing to broader environmental benefits. By reducing the need for multiple launches and enabling more efficient missions, fusion propulsion can lower the overall carbon footprint of space exploration. This efficiency supports global efforts to mitigate climate change and promote sustainable practices. Public perception of fusion propulsion is generally positive due to its clean energy profile. This support can drive further investment and development, accelerating the transition to more environmentally friendly propulsion methods in space. Fusion propulsion aligns with international goals for sustainable development and environmental protection. As space exploration expands, adopting technologies with minimal environmental impact is crucial for maintaining ecological balance. The long-term benefits of fusion propulsion extend beyond space travel. By pioneering clean and efficient energy technologies, fusion propulsion can set a precedent for sustainable innovation, inspiring future generations to prioritize environmental stewardship in all technological endeavors. The longevity and durability of fusion engines are critical factors that determine their viability for long-term space missions. Fusion engines are designed to operate continuously over extended periods, providing sustained thrust for deep space exploration. One of the primary advantages of fusion engines is their ability to function for years without the need for refueling. The high energy density of fusion fuel means that a relatively small amount can power a spacecraft for prolonged missions. Durability in the harsh environment of space is essential for the success of fusion propulsion. Fusion engines must withstand extreme temperatures, radiation, and mechanical stresses without degrading in performance. Advanced materials play a crucial role in ensuring the longevity of fusion engines. These materials must resist the intense heat and radiation produced by fusion reactions, maintaining their structural integrity over the engine's operational life. Innovations in heat management systems are vital for protecting fusion engines. Efficient cooling mechanisms are required to dissipate the immense heat generated, preventing damage to the reactor components and ensuring continuous operation. Magnetic confinement systems used in fusion engines must be robust and reliable. These systems create powerful magnetic fields to contain the hot plasma, and their performance is critical to sustaining fusion reactions over long durations. Regular maintenance and remote repair capabilities are essential for maintaining the longevity of fusion engines. Spacecraft equipped with fusion propulsion may include systems for diagnosing and addressing issues without requiring human intervention. The design of fusion engines also incorporates redundancy to enhance reliability. Multiple subsystems and backup components ensure that the engine can continue to operate even if one part fails, reducing the risk of mission failure. Long-term testing and validation are necessary to prove the durability of fusion engines. Simulating extended missions and exposing engines to the conditions they will face in space helps identify potential weaknesses and areas for improvement. The operational lifespan of fusion engines is expected to surpass that of chemical and fission propulsion systems. Their ability to provide continuous thrust and power over many years makes them ideal for missions to distant planets and interstellar travel. Fusion engines' resilience to radiation is another advantage. The materials and designs used in fusion reactors are chosen to withstand the high levels of radiation encountered in deep space, ensuring consistent performance. The modular design of fusion engines can facilitate upgrades and repairs. Modules can be replaced or enhanced with newer technologies as they become available, extending the overall lifespan of the propulsion system. Energy efficiency contributes to the durability of fusion engines. By maximizing the energy extracted from fusion reactions, these engines can operate more efficiently, reducing wear and tear on components. The potential for using fusion engines in multiple missions also enhances their value. After completing one mission, a well-maintained fusion engine could be refurbished and reused for future explorations, offering cost savings and increased sustainability. The longevity and durability of fusion engines are key to unlocking new possibilities in space travel. Their robust performance, coupled with advanced materials and systems, ensures that fusion propulsion will play a pivotal role in the future of interstellar exploration. Cost considerations and economic feasibility are crucial aspects of developing fusion propulsion. While the initial investment in research and development is significant, the long-term benefits could outweigh these costs. Fusion propulsion systems require advanced technology and materials, which can be expensive. However, the high efficiency and reduced fuel requirements of fusion engines may lower operational costs over time. The development phase involves substantial financial input from governments, private companies, and international collaborations. Securing sustained funding is essential to support the ongoing research and technological advancements needed for fusion propulsion. One of the primary cost benefits of fusion propulsion is the reduced need for fuel. Fusion engines use small amounts of deuterium and tritium, which are more abundant and cheaper to procure than traditional chemical fuels. The high energy density of fusion fuel means that missions can be planned with fewer launches, reducing the overall costs associated with multiple launches and the logistics of transporting large quantities of fuel. Maintenance and longevity of fusion engines contribute to their economic feasibility. Fusion engines are designed for long-term use, which can spread the initial investment over many years and multiple missions, providing better returns on investment. Reusable components in fusion propulsion systems can further enhance economic feasibility. By designing engines that can be refurbished and reused, the overall cost of space missions can be significantly reduced. Economic feasibility also depends on scaling up production. As fusion technology matures, mass production of components and reactors can lower costs through economies of scale, making fusion propulsion more accessible. Initial costs for building and testing fusion reactors are high, but these expenses can be mitigated by the long-term savings in fuel and operational efficiency. The reduced environmental impact and sustainability of fusion propulsion also add to its economic value. International collaborations can share the financial burden and pool resources, making the development of fusion propulsion more economically viable. Shared knowledge and technology can accelerate progress and reduce costs for individual stakeholders. The potential for dual-use technology in fusion propulsion adds to its economic appeal. Innovations developed for space propulsion can have applications in other industries, such as energy production and materials science, providing additional revenue streams. Investing in fusion propulsion can drive technological advancements and stimulate economic growth. The development of new technologies and infrastructure can create jobs and foster industries related to advanced materials, energy, and aerospace. Public and private investments in fusion technology reflect its perceived economic potential. As the technology progresses and demonstrates feasibility, more investors are likely to support its development, further reducing financial barriers. The cost-benefit analysis of fusion propulsion must also consider the long-term advantages for space exploration. The ability to undertake longer, more ambitious missions with reduced fuel requirements can lead to groundbreaking scientific discoveries and commercial opportunities. Ultimately, the economic feasibility of fusion propulsion hinges on a combination of technological success, sustained investment, and the ability to scale production. As these elements come together, fusion propulsion has the potential to revolutionize space travel both economically and technologically. Potential speeds achievable with fusion propulsion are one of its most exciting aspects. Fusion engines can generate continuous thrust over extended periods, allowing spacecraft to reach much higher velocities than with traditional propulsion systems. Current chemical rockets provide high thrust, but for short durations, limiting their speeds. Fusion propulsion, with its ability to sustain thrust, could achieve speeds necessary for deep space exploration and interstellar travel. Calculations suggest that fusion-powered spacecraft could reach a significant fraction of the speed of light. Speeds of 10% to 20% of light speed are theoretically possible, drastically reducing travel times to distant stars. For missions within our solar system, Fusion propulsion could enable rapid transit. A trip to Mars, which currently takes about 6 to 9 months with chemical rockets, could be shortened to just a few weeks with fusion engines. Travel to the outer planets, such as Jupiter or Saturn, could also see dramatic reductions in time. What now takes several years could be accomplished in a matter of months, opening up more frequent and detailed exploration opportunities. Fusion propulsion could enable missions to explore the Kuiper Belt and the Oort cloud. These distant regions, currently beyond practical reach, could be investigated within human lifetimes using fusion technology. The continuous acceleration capability of fusion engines means spacecraft can build up speed over time, unlike chemical rockets which burn fuel quickly and coast. This results in higher final velocities for long-duration missions. The potential to reach nearby star systems, such as Alpha Centauri, becomes more feasible with fusion propulsion. While current technology would take thousands of years, fusion propulsion could shorten this to mere decades. Fusion propulsion also offers the potential for faster return missions. Scientific missions to gather samples from distant moons or asteroids could be completed more quickly, with valuable data and materials returned to Earth in a shorter time frame. High speeds achievable with fusion propulsion enhance mission flexibility. Spacecraft can perform complex maneuvers and course corrections more efficiently, adapting to new discoveries or mission requirements in real time. Faster speeds reduce the time astronauts spend exposed to cosmic radiation and microgravity, addressing some of the significant health risks associated with long-duration space travel. This is crucial for the safety and well-being of crewed missions. The increased speed capabilities open up the possibility of real-time communication and control for robotic missions in distant regions of space. Faster travel times mean data and instructions can be sent and received more quickly, enhancing mission success. Fusion propulsion can support ambitious scientific goals, such as detailed studies of the outer planets, their moons, and even missions to interstellar objects passing through our solar system. High speeds make these targets more accessible. The ability to travel faster also means we can deploy and resupply space infrastructure more efficiently. Space stations, habitats on the Moon or Mars, and even space-based telescopes can benefit from rapid deployment and support missions. Ultimately, the potential speeds achievable with fusion propulsion could transform our approach to space exploration. By significantly reducing travel times and expanding the range of accessible destinations, fusion propulsion will enable humanity to explore and settle new frontiers in space. The impact of fusion propulsion on travel time to Mars and beyond is profound. Traditional chemical rockets take 6 to 9 months to reach Mars, but fusion engines could reduce this journey to just a few weeks. Shortening the travel time to Mars has significant benefits for crewed missions. Astronauts would spend less time exposed to the hazards of space, such as cosmic radiation and microgravity, reducing health risks. Faster travel times also mean that missions can be more flexible and responsive. Scientists could send missions to explore specific events or phenomena on Mars with less advanced planning, increasing the scientific return. Fusion propulsion's continuous thrust capability means spacecraft can decelerate more effectively upon arrival. This allows for more precise entry into Mars's orbit or direct landing approaches, enhancing mission safety and accuracy. For missions beyond Mars, such as to the asteroid belt or Jupiter, fusion propulsion offers similar reductions in travel time. These missions currently take years, but could be completed in months with fusion technology. The ability to reach the outer planets faster opens up new opportunities for exploration. Missions to study Jupiter's moon Europa, believed to have a subsurface ocean, could gather data more quickly and return it to Earth in a shorter time frame. Traveling to Saturn and its moon Titan, with its thick atmosphere and lakes of liquid methane, could become more feasible. Fusion propulsion would make these distant destinations more accessible for detailed scientific study. Missions to the Kuiper Belt, where objects like Pluto reside, would also benefit. What now takes over a decade could be accomplished in a few years, allowing for more frequent and comprehensive exploration of this distant region. Fusion propulsion could revolutionize missions to interstellar space. The Voyager probes took decades to reach the edge of our solar system, but fusion-powered spacecraft could make the journey in a fraction of that time. Exploration of the Oort cloud, a distant reservoir of comets, could be significantly accelerated. This region, currently beyond practical reach, could be studied within human lifetimes, offering insights into the early solar system. Reducing travel time also means that return missions, such as sample return missions from Mars or other celestial bodies, can be completed more quickly. This accelerates the pace of scientific discovery and allows for faster analysis of extraterrestrial materials. Shorter travel times enhance mission feasibility for robotic and crewed exploration alike. The logistics of supplying and supporting long-duration missions become more manageable with faster transit. For commercial space ventures, such as mining asteroids for resources, the reduced travel time improves economic viability. Faster missions mean quicker returns on investment and more efficient operations. International collaboration on space missions can benefit from fusion propulsion. With reduced travel times, joint missions involving multiple countries can be coordinated more effectively, enhancing global cooperation in space exploration. Ultimately, the impact of fusion propulsion on travel time to Mars and beyond transforms the scope and ambition of space missions. By enabling faster and more efficient travel, fusion propulsion brings the dream of exploring and settling distant worlds closer to reality. The feasibility of interstellar travel hinges significantly on advancements in propulsion technology, with fusion propulsion being a promising candidate. Fusion propulsion could provide the high speeds necessary to make interstellar journeys within human lifetimes a reality. Current propulsion methods, like chemical rockets, are not viable for interstellar travel due to their limited speed and fuel efficiency. Fusion propulsion, however, offers continuous thrust and high efficiency, making it a game-changer for reaching distant stars. One of the key challenges in interstellar travel is the vast distance between stars. The closest star system, Alpha Centauri, is over 4 light-years away. Fusion propulsion could potentially cut travel time from thousands of years to a few decades. Achieving a fraction of the speed of light is essential for feasible interstellar travel. Fusion propulsion's ability to provide sustained thrust could allow spacecraft to reach speeds of up to 10 to 20% of light speed, significantly reducing travel time. Energy requirements for such missions are immense, but fusion reactions provide a high energy yield from relatively small amounts of fuel. This efficiency is crucial for carrying sufficient fuel and supplies for long-duration missions. Advanced shielding and radiation protection will be necessary to protect spacecraft and crew from cosmic rays and other interstellar hazards. Fusion-powered spacecraft could incorporate these technologies to ensure the safety of long-term missions. The development of autonomous and self-repairing systems is critical for interstellar travel. Fusion propulsion systems will need to operate reliably for decades, with minimal human intervention to reach distant star systems. Interstellar travel also requires robust life support systems. Fusion propulsion can provide continuous power, supporting life support systems and scientific instruments throughout the journey. Navigational technology must also advance to enable precise interstellar travel. Fusion propulsion allows for mid-course corrections and fine-tuning of the spacecraft's trajectory, which is essential for reaching specific destinations. Exploration of exoplanets becomes more feasible with fusion propulsion. Potentially habitable planets orbiting nearby stars could be studied in detail, opening up new possibilities for finding life beyond our solar system. Fusion propulsion can support large, multi-generational spacecraft. These vessels would carry everything needed for long-term survival and exploration, making the concept of human colonies traveling to other star systems more plausible. The cost of developing and launching interstellar missions is currently prohibitive, but the long-term benefits of fusion propulsion, such as reduced fuel needs and increased efficiency, could make these missions more economically viable. International collaboration and investment are crucial for the success of interstellar missions. Combining resources and expertise from multiple countries can accelerate the development of fusion propulsion and the associated technologies needed for interstellar travel. Theoretical studies and simulations are already exploring the potential of fusion propulsion for interstellar travel. These studies help identify technical challenges and guide the design of future spacecraft capable of reaching distant stars. Ultimately, the feasibility of interstellar travel depends on our ability to overcome significant technical and logistical challenges. Fusion propulsion represents a promising step forward, offering the potential to transform humanity into an interstellar civilization. The impact of fusion propulsion on mission planning and logistics is transformative. Fusion engines' high efficiency and continuous thrust capabilities simplify mission design, reducing the complexity of planning long-duration spaceflights. Traditional chemical rockets require precise timing and alignment with planetary positions to minimize fuel consumption. Fusion propulsion's sustained thrust allows for more flexible launch windows, easing the constraints on mission timing. With fusion propulsion, spacecraft can take more direct routes to their destinations, rather than relying on gravity assists and complex orbital maneuvers. This direct approach shortens travel times and streamlines mission planning. The reduced need for large quantities of fuel simplifies spacecraft design and launch logistics. Lighter spacecraft can carry more scientific instruments, crew supplies, or additional payload, enhancing mission objectives and capabilities. Fusion propulsion's continuous power supply supports advanced life support systems, scientific instruments, and onboard manufacturing or repair facilities. This self-sufficiency is crucial for long-term missions far from Earth. The ability to perform mid-course corrections with fusion engines enhances mission adaptability. Spacecraft can adjust their trajectories in response to new discoveries or changing mission parameters, increasing the likelihood of mission success. Longer missions become more feasible with fusion propulsion. The sustained thrust and high energy efficiency allow for extended exploration of multiple targets within a single mission, maximizing scientific returns. Fusion propulsion reduces the dependency on in situ resource utilization. Spacecraft can carry sufficient supplies for the entire mission, avoiding the need to extract resources from other celestial bodies, which simplifies mission logistics and reduces risks. The development of fusion propulsion technology encourages international collaboration. Shared missions leveraging fusion engines can distribute costs, share expertise, and foster cooperation in space exploration, leading to more ambitious and successful projects. Maintenance and repair logistics benefit from fusion propulsion's continuous power supply. Spacecraft can be equipped with autonomous repair systems, ensuring long-term operational integrity and reducing the need for frequent resupply missions. Fusion propulsion also impacts crewed mission planning by improving safety and comfort. Shorter travel times reduce the exposure of astronauts to harmful space radiation and the psychological effects of prolonged isolation, enhancing crew well-being and performance. The reliability of fusion engines supports the development of deep space habitats and research stations. These long-term outposts can be supplied and maintained more effectively, supporting continuous human presence in space. For commercial missions, fusion propulsion lowers operational costs and increases profitability. The ability to reach and exploit resources from asteroids or other celestial bodies more efficiently opens new avenues for space-based industries. The scalability of fusion propulsion technology means that future missions can be progressively more complex and ambitious. As the technology matures, larger and more capable spacecraft can be designed, supporting a wider range of exploration and commercial activities. Ultimately, the integration of fusion propulsion into mission planning and logistics transforms the scope and scale of what is possible in space exploration. By enabling faster, more efficient and flexible missions, fusion propulsion paves the way for a new era of discovery and human presence in the cosmos. Comparing fusion propulsion with current propulsion systems highlights its transformative potential. Chemical propulsion, the most common method today, provides high thrust but is limited by low efficiency and the need for large amounts of fuel. Chemical rockets generate thrust through combustion, releasing energy quickly and providing the force needed to escape Earth's gravity. However, this rapid fuel consumption limits their usefulness for long-duration missions. Electric propulsion systems, such as ion thrusters, offer higher efficiency than chemical rockets, but produce low thrust. They are ideal for long-duration missions where gradual acceleration is acceptable, but they cannot lift heavy payloads from planetary surfaces. Nuclear fission propulsion provides higher thrust and efficiency than chemical propulsion. Systems like nuclear thermal rockets can heat propellant to produce thrust, but they come with significant safety and regulatory challenges due to radioactive materials. Fusion propulsion combines the best aspects of these technologies. It offers high thrust like chemical rockets and sustained efficiency like electric propulsion, without the long-lived radioactive waste associated with fission. The specific impulse of fusion propulsion is significantly higher than that of chemical rockets, meaning it can produce more thrust per unit of fuel. This higher efficiency allows for longer missions with less fuel, reducing overall mission costs. Fusion propulsion also enables continuous thrust, unlike the short bursts provided by chemical rockets. This continuous acceleration allows spacecraft to reach higher speeds, reducing travel times to distant destinations. Compared to electric propulsion, fusion engines can provide much greater thrust, making them suitable for a wider range of missions, including those requiring quick acceleration and heavy payloads. Fusion propulsion's fuel, primarily isotopes of hydrogen, is more abundant and easier to handle than the enriched uranium needed for fission propulsion. This abundance makes fusion a more sustainable and cost-effective option in the long term. The environmental impact of fusion propulsion is also favorable. Fusion reactions produce minimal, long-lived radioactive waste, unlike fission, and do not release harmful pollutants like chemical rockets. Safety is another key advantage. Fusion reactors do not carry the same risk of catastrophic failure as chemical rockets or fission reactors. The reaction can be quickly stopped by cutting off the fuel supply, minimizing the risk of accidents. Fusion propulsion systems also offer greater flexibility in mission planning. The ability to perform mid-course corrections and adjust trajectories in real time enhances mission adaptability and success rates. The continuous power supply from fusion engines supports advanced onboard systems, including life support, scientific instruments, and autonomous repair systems. This capability is crucial for long-duration missions far from Earth. Economically, fusion propulsion promises lower operational costs over time. The reduced need for frequent resupply missions, combined with the ability to carry more payload, improves the financial feasibility of ambitious space exploration projects. Ultimately, the comparison with current propulsion systems underscores the revolutionary potential of fusion propulsion. By addressing the limitations of chemical, electric, and fission propulsion, fusion offers a path to more efficient, sustainable, and ambitious space exploration. The safety of fusion reactors in space is a critical consideration. Fusion reactors are designed with several inherent safety features that make them suitable for space missions. One of the primary safety advantages of fusion reactors is the absence of a chain reaction. Unlike fission reactors, fusion does not rely on a self-sustaining chain reaction, which reduces the risk of a runaway reaction or meltdown. Fusion reactions require precise conditions to be maintained. If these conditions are disrupted, the reaction simply stops, making fusion reactors inherently stable and controllable. The fuel used in fusion reactors, such as deuterium and tritium, poses less of a radiation hazard compared to the enriched uranium or plutonium used in fission reactors. This reduces the potential for harmful radiation exposure. Fusion reactors produce minimal, long-lived radioactive waste. The primary byproduct, helium, is inert and non-toxic, eliminating the need for complex waste management systems. Shielding is still necessary to protect against neutron radiation generated during fusion reactions. Advances in material science are developing effective shielding solutions that are lightweight and suitable for space environments. The modular design of fusion reactors allows for redundant safety systems. Multiple layers of protection can be incorporated to ensure that if one system fails, others can take over to maintain safe operation. Remote monitoring and control systems enhance the safety of fusion reactors in space. These systems allow for real-time oversight and adjustments to reactor operations from mission control on Earth or by onboard automated systems. In the event of a malfunction, fusion reactors can be rapidly shut down by cutting off the fuel supply. This quick response capability is crucial for maintaining safety during space missions. Fusion reactors also have fewer moving parts compared to mechanical propulsion systems. This simplicity reduces the risk of mechanical failures and increases overall reliability. Robust cooling systems are integral to the safe operation of fusion reactors. Efficient heat dissipation ensures that the reactor components do not overheat, preventing damage and maintaining stable operation. Safety protocols for handling and storing fusion fuel are well established. Deuterium and tritium can be safely stored and transported using existing technologies, minimizing risks during launch and operation. The development of fusion reactors includes rigorous testing and validation under simulated space conditions. This testing ensures that reactors can withstand the stresses and challenges of space environments. International cooperation on fusion research contributes to safety standards. shared knowledge and best practices help develop comprehensive safety protocols for operating fusion reactors in space. The inherent safety features of fusion reactors, combined with advanced materials, robust systems, and international collaboration, ensure that fusion propulsion is a safe and reliable option for future space missions. Radiation protection and shielding are essential for the safe operation of fusion reactors in space. The primary concern is neutron radiation, which is produced during fusion reactions and can pose a risk to both spacecraft and crew. Effective shielding materials are crucial to absorb and deflect neutron radiation. Researchers are developing advanced materials, such as boron carbide and tungsten, that offer high neutron absorption capabilities while being lightweight and durable. The design of the spacecraft itself can incorporate these materials in strategic locations. For instance, placing shielding around the reactor core and critical systems can protect both the equipment and the crew. Multi-layered shielding is another effective approach. Combining different materials, each optimized to absorb specific types of radiation, can enhance overall protection. This method ensures that neutrons are effectively captured and dispersed. Hydrogen-rich materials such as polyethylene are particularly effective at slowing down and absorbing neutrons. These materials can be used in conjunction with metal alloys to provide comprehensive protection. The placement of fuel and water tanks around the reactor can also serve as an additional layer of shielding. These tanks not only store essential supplies, but also contribute to the spacecraft's radiation protection system. Active radiation protection systems are being explored to complement passive shielding. These systems use electromagnetic fields to deflect charged particles, offering another line of defense against radiation. Monitoring radiation levels in real time is vital for ensuring safety. Advanced sensors can detect neutron radiation and provide immediate feedback, allowing for adjustments to shielding configurations as needed. Robust data collection from these sensors can also help refine shielding designs for future missions. By analyzing radiation exposure in various conditions, engineers can develop more effective protection strategies. Radiation protection extends to the design of crew habitats. Incorporating shielding materials into walls and floors can create safe living and working environments, reducing the crew's exposure to harmful radiation. Personal protective equipment, such as radiation suits, can offer an additional layer of defense for astronauts when they are required to work near the reactor or in other high radiation areas. During periods of high solar activity, such as solar flares, additional precautions can be taken. The crew can be directed to more heavily shielded areas of the spacecraft, minimizing their exposure to increased radiation levels. Advancements in nanotechnology hold promise for developing new shielding materials. Nanomaterials with high radiation absorption properties can be integrated into the spacecraft structure, providing effective protection with minimal added weight. International collaboration on radiation protection research enhances the development of effective shielding solutions. Sharing data and best practices ensures that all spacefaring nations benefit from the latest advancements in radiation safety. By combining advanced materials, innovative design strategies, and active protection systems, we can ensure that fusion-powered spacecraft are safe from radiation, enabling longer and more ambitious missions into deep space. Handling of fusion fuel is a critical aspect of operating fusion propulsion systems. The primary fuels, deuterium and tritium, require careful management to ensure safety and efficiency. Deuterium is a stable isotope of hydrogen and is relatively easy to handle. It can be extracted from seawater using established chemical processes, making it a readily available and abundant fuel source. Tritium, on the other hand, is a radioactive isotope with a half-life of about 12 years. It must be produced in reactors or extracted from natural sources in small quantities, requiring special handling procedures to manage its radioactivity. Storing tritium involves using specially designed containers that prevent the escape of radiation. These containers are typically made from materials that absorb beta particles emitted by tritium, ensuring safe storage and transport. During fusion reactor operation, tritium can be bred from lithium. When lithium absorbs neutrons produced during fusion, it forms tritium, creating a self-sustaining fuel cycle that reduces the need for external tritium supplies. Fuel handling systems on spacecraft must include robust safety features. Automated systems can monitor fuel levels, detect leaks, and control the flow of deuterium and tritium to the reactor, ensuring safe and efficient operation. Specialized pumps and valves are used to transfer deuterium and tritium from storage tanks to the reactor. These components must be designed to withstand the harsh conditions of space and the specific properties of the fuels. Inert gas environments, such as helium, can be used to minimize the risk of chemical reactions with fusion fuels. This practice helps maintain fuel purity and prevents unwanted reactions that could compromise safety. Regular maintenance and inspection of fuel handling systems are essential to ensure their integrity and performance. Scheduled checks can identify potential issues before they become critical, maintaining the overall safety of the mission. Training for crew members includes detailed protocols for handling fusion fuels, understanding the properties of deuterium and tritium, along with proper safety measures, ensures that the crew can manage the fuel safely and respond effectively to any incidents. In the event of a fuel leak, rapid containment measures are necessary. Emergency procedures might involve isolating affected areas, venting contaminated atmospheres into space, and using robotic systems to repair leaks. The integration of remote monitoring systems allows mission control on Earth to oversee fuel handling operations. Real-time data transmission enables experts to provide guidance and support, enhancing the safety and efficiency of the mission. Developing international standards for fusion fuel handling ensures consistency and safety across all space missions. Collaborative efforts can lead to best practices that protect both crew and spacecraft. Research into alternative fusion fuels, such as helium-3, continues. These fuels could offer advantages in terms of safety and efficiency, potentially simplifying fuel handling procedures in the future. By implementing rigorous safety protocols and leveraging advanced technology, the handling of fusion fuel can be managed effectively. This ensures the safe operation of fusion propulsion systems and the success of future space missions. Risks associated with fusion propulsion systems in space are diverse, but effective mitigation strategies can address these challenges. Understanding these risks is crucial for ensuring the safety and success of fusion-powered missions. One primary risk is the potential for radiation exposure from neutron emissions. Shielding materials like boron carbide and tungsten are used to absorb and deflect neutrons, protecting both the spacecraft and its crew. Thermal management is another critical concern. Fusion reactions generate immense heat, which must be dissipated to prevent damage. Advanced cooling systems using heat exchangers and radiators are essential for maintaining stable reactor temperatures. Structural integrity of the fusion reactor is vital. High temperatures and radiation can weaken materials over time. Using advanced alloys and composites that withstand extreme conditions ensures the longevity and safety of the reactor. Fuel handling poses a risk due to the radioactive nature of tritium. Secure storage containers and automated handling systems minimize human exposure and prevent leaks, maintaining a safe operating environment. Potential fuel leaks or spills must be addressed swiftly. Containment protocols involve isolating affected areas and using automated systems to clean up spills, preventing the spread of radioactive material. Reactor malfunctions, though unlikely, require immediate response strategies. Automated shutdown procedures and redundant safety systems can quickly halt the fusion reaction, preventing further complications. Crew training is essential for managing these risks. Astronauts must be well versed in safety protocols, emergency procedures, and the operation of fusion propulsion systems to effectively handle any issues that arise. Remote monitoring enhances safety by allowing mission control to oversee operations and provide guidance. Real-time data on reactor performance and environmental conditions helps identify and address problems promptly. Cybersecurity is another important consideration. Protecting the fusion reactor's control systems from cyber threats ensures that malicious actors cannot disrupt operations or cause failures. Regular maintenance and inspections are crucial for identifying potential issues before they become critical. Scheduled checks of the reactor and associated systems help maintain optimal performance and safety. International collaboration on safety standards and best practices can improve risk management. Sharing knowledge and strategies across space agencies and organizations fosters a comprehensive approach to safety. Advanced simulation and testing of fusion propulsion systems under realistic conditions help identify potential failure points and refine mitigation strategies. ensuring the reliability and safety of these systems. Public perception and acceptance of fusion technology rely on demonstrating its safety and effectiveness. Transparent communication about risks and mitigation strategies builds trust and support for fusion propulsion initiatives. Continuous research and development are necessary to enhance safety measures. Innovations in materials science, reactor design, and emergency response technologies contribute to the ongoing improvement of fusion propulsion systems. By implementing these mitigation strategies, the risks associated with fusion propulsion can be effectively managed, paving the way for safe and successful space missions. Regulatory and policy implications for fusion propulsion are complex and multifaceted. Establishing a robust regulatory framework is essential to ensure safety and compliance with international standards. The development and deployment of fusion propulsion systems require adherence to existing space treaties. These treaties, such as the Outer Space Treaty, govern the peaceful use of outer space and mandate the prevention of harmful contamination. Nuclear safety regulations play a crucial role. Fusion propulsion involves handling radioactive materials, necessitating strict compliance with international nuclear safety standards to protect both space and terrestrial environments. Licensing and certification processes must be developed for fusion propulsion systems. These processes ensure that all systems meet rigorous safety and performance standards before deployment. International cooperation is vital for regulatory success. Spacefaring nations and organizations need to collaborate on creating and enforcing standards, sharing best practices, and fostering mutual trust. The environmental impact of fusion propulsion must be considered. Policies should address the mitigation of any potential environmental hazards, ensuring that space exploration remains sustainable and responsible. Liability and insurance frameworks are necessary to manage the risks associated with fusion propulsion. These frameworks protect stakeholders in the event of accidents or malfunctions, ensuring accountability and compensation. Export controls and technology transfer regulations are crucial for managing the dissemination of fusion propulsion technology. These controls prevent the misuse of advanced propulsion systems and safeguard national security. Public engagement and transparency in the regulatory process build trust and support for fusion propulsion initiatives. Clear communication about the benefits, risks, and safety measures fosters public confidence. Policies should incentivize research and development in fusion propulsion. Funding and grants can accelerate technological advancements and encourage private sector investment, driving innovation in the field. Space traffic management regulations must be updated to accommodate fusion-propelled spacecraft. These regulations ensure the safe and efficient operation of spacecraft in increasingly crowded orbital environments. Intellectual property rights need to be clearly defined. Protecting innovations in fusion propulsion technology encourages further research and development by ensuring inventors and companies can benefit from their work. Training and certification for personnel handling fusion propulsion systems are essential. Regulatory frameworks should mandate comprehensive training programs to ensure the highest levels of expertise and safety. Continuous review and adaptation of regulations are necessary to keep pace with technological advancements. As fusion propulsion technology evolves, so too must the policies and regulations governing its use. By addressing these regulatory and policy implications, we can create a safe, sustainable, and cooperative environment for the development and deployment of fusion propulsion systems, enabling humanity to explore the cosmos responsibly. Fusion propulsion has the potential to significantly expand human presence in the solar system. By reducing travel times, it opens up new possibilities for exploration and colonization. Mars, our next major target, could become more accessible. Fusion propulsion can shorten the journey to a matter of weeks, making regular missions and even permanent settlements feasible. The Moon could see increased activity as well. Faster travel times and efficient propulsion would support the construction of lunar bases, serving as hubs for further exploration. Asteroids and the asteroid belt hold valuable resources. Fusion propulsion enables missions to these distant objects, facilitating mining operations and resource extraction that support space industries. Jupiter's moons, such as Europa and Ganymede, become reachable destinations. The potential for finding life and conducting scientific research on these icy worlds is greatly enhanced by faster travel. Saturn's moon Titan, with its thick atmosphere and hydrocarbon lakes, offers unique opportunities for exploration. Fusion propulsion could make regular missions to Titan a reality, expanding our understanding of this fascinating moon. Long-term habitats on these moons would benefit from the continuous supply capabilities of fusion propulsion, ensuring the steady delivery of supplies and equipment necessary for sustained human presence. The Kuiper Belt, home to Pluto and other distant objects, becomes more accessible. Missions to study these ancient remnants of the solar system can be conducted more frequently, providing new insights into our cosmic neighborhood. Fusion propulsion supports the development of space infrastructure. Space stations, refueling depots, and research facilities can be established throughout the solar system, creating a network that supports deeper exploration. Human presence on multiple celestial bodies fosters international collaboration. Joint missions and shared facilities enhance cooperation and contribute to global peace and scientific progress. The ability to transport large payloads efficiently supports construction projects in space. Building habitats, research stations, and other infrastructure becomes more feasible with the capabilities of fusion propulsion. Fusion propulsion also facilitates the establishment of self-sustaining colonies. These colonies could produce their own food, water, and energy, reducing dependence on Earth and enhancing long-term viability. Exploring the outer planets and their moons provides opportunities for scientific discovery. Understanding the geology, atmospheres, and potential for life in these distant worlds expands our knowledge of the solar system. The expansion of human presence supports economic growth. Space tourism, mining, and other commercial activities become viable industries, contributing to a space-based economy. Ultimately, fusion propulsion drives humanity's transition to a multiplanetary species. By enabling faster and more efficient travel throughout the solar system, it ensures that our future lies not just on Earth, but among the stars. Fusion propulsion could revolutionize crewed missions to Mars by significantly reducing travel time. Current missions take 6 to 9 months, but fusion engines could cut this down to a matter of weeks. Shorter travel times would mitigate the health risks associated with prolonged exposure to cosmic radiation and microgravity. Astronauts would arrive on Mars in better physical condition, ready to carry out their missions. The reduced travel duration also decreases the psychological strain on the crew. Spending less time confined in a spacecraft minimizes isolation and stress, improving overall mental well-being. Fusion propulsion allows for more flexible launch windows. Missions wouldn't be as dependent on planetary alignments, enabling more frequent and timely departures and returns. Enhanced propulsion capabilities mean larger payloads can be transported to Mars. This allows for more comprehensive scientific equipment, life support systems, and supplies, supporting longer and more complex missions. The ability to carry more cargo also facilitates the establishment of sustainable habitats on Mars. These habitats would be equipped with all necessary resources, ensuring the crew's safety and comfort during extended stays. Reliable and efficient propulsion increases the feasibility of emergency return missions. If a situation arises that requires the crew to return to Earth quickly, fusion propulsion provides the necessary speed and reliability. Fusion-powered spacecraft could support multiple missions within the same journey. Crews could explore different regions of Mars, conducting a wider range of scientific experiments and geological surveys. The continuous power supply from fusion reactors supports advanced life support systems. This ensures a stable environment for the crew, with reliable air, water, and food production systems. Fusion propulsion can also support in-situ resource utilization on Mars. By transporting the necessary equipment, crews can produce fuel, water, and other essentials on the Martian surface, reducing dependence on supplies from Earth. With fusion propulsion, Mars missions can carry advanced medical facilities and equipment. This ensures that astronauts have access to comprehensive medical care, enhancing their safety and well-being. Increased cargo capacity allows for more robust communication systems. Reliable and high-speed communication with Earth is essential for mission success, enabling real-time data transmission and support. The flexibility and reliability of fusion propulsion encourage international collaboration. Joint missions to Mars can share the benefits of this advanced technology, fostering cooperation and mutual progress in space exploration. Fusion propulsion supports the concept of a Mars exploration hub. Crewed missions can establish a central base on Mars, from which multiple exploratory missions can be launched to various parts of the planet. Ultimately, the impact of fusion propulsion on crewed missions to Mars is profound. By providing faster, safer, and more efficient travel, it paves the way for a sustained human presence on the red planet, opening new frontiers for exploration and discovery. Fusion propulsion offers tremendous potential for establishing lunar bases and extending human presence beyond the Moon. The efficiency and power of fusion engines make regular missions to the Moon more feasible. Lunar bases could serve as testing grounds for fusion propulsion technology, demonstrating its capabilities and reliability in a relatively close and controlled environment. The reduced travel time enabled by fusion propulsion allows for frequent resupply missions to the Moon. This ensures that lunar bases have a continuous supply of necessary resources and equipment. With the ability to transport larger payloads, fusion propulsion supports the construction of more extensive and sophisticated lunar habitats. These habitats can house more crew members and provide better living conditions. Fusion-powered missions can facilitate the establishment of scientific research stations on the Moon. These stations can conduct long-term studies of the lunar surface, geology, and potential resources. The Moon can act as a launch platform for deeper space missions. Fusion propulsion can efficiently ferry equipment and personnel between Earth, the Moon, and beyond, creating a network of interconnected bases. Using the Moon's resources, such as water ice, becomes more practical with fusion propulsion. The energy provided by fusion reactors can power extraction and processing facilities, supporting sustainable lunar living. Fusion propulsion also enhances the potential for lunar tourism. Shorter travel times and more reliable missions make it possible to develop a lunar tourism industry, offering new commercial opportunities. Beyond the Moon, fusion propulsion can enable missions to asteroids for mining operations. Asteroids contain valuable materials that can be used for construction, fuel, and other purposes, supporting a space-based economy. The same technology that makes lunar bases possible can be adapted for bases on Mars and other celestial bodies. Fusion propulsion provides the flexibility and power needed for these ambitious projects. Establishing bases on other moons, such as those of Jupiter and Saturn, becomes feasible. Fusion propulsion can support long-duration missions to these distant targets, opening up new frontiers for exploration. Fusion-powered spacecraft can transport infrastructure for building space habitats. These habitats can serve as way stations or colonies, supporting human life in deep space. With reliable and efficient propulsion, a network of bases and habitats throughout the solar system can be developed. This network enhances humanity's ability to explore, study, and utilize space resources. The potential for fusion propulsion extends to missions aimed at the outer planets. Bases on moons like Europa or Titan can be supplied and supported, enabling in-depth scientific exploration of these intriguing worlds. Ultimately, fusion propulsion can transform humanity's approach to space exploration. By enabling the establishment of lunar bases and beyond, it paves the way for a sustainable and expansive human presence throughout the solar system. Fusion propulsion is a key technology for enabling deep space exploration. Its high efficiency and sustained thrust capabilities make it ideal for long-duration missions to distant targets. Traditional propulsion systems are limited by their fuel requirements and short burn times. Fusion propulsion, however, can provide continuous thrust, allowing spacecraft to reach higher velocities over time. This continuous acceleration is crucial for exploring deep space, where distances are vast and travel times are measured in years or even decades. Fusion propulsion reduces these times significantly. Missions to the outer planets, such as Jupiter, Saturn, Uranus, and Neptune, become more feasible with fusion propulsion. These missions can carry more scientific instruments and return more data than ever before. Exploring the Kuiper Belt and the Oort Cloud, regions filled with ancient and distant objects, becomes practical. Fusion propulsion can support missions that venture far beyond the orbit of Pluto. Interstellar missions, once the stuff of science fiction, become a real possibility. Fusion propulsion could power probes to nearby star systems, like Alpha Centauri, within a human lifetime. Deep space exploration benefits from the continuous power supply provided by fusion reactors. This power can support advanced scientific instruments, communication systems, and life support for crewed missions. Fusion propulsion can carry larger payloads, enabling more comprehensive scientific studies. Missions can include rovers, landers, and other equipment to explore planetary surfaces and atmospheres in detail. Long-term missions require sustainable life support systems. Fusion propulsion supports the development of closed-loop life support, providing a steady supply of energy for air, water, and food production. Autonomous and robotic systems benefit from fusion propulsion's capabilities. These systems can explore harsh and distant environments, collecting data and performing tasks that would be impossible for humans. The potential for sample return missions from distant celestial bodies increases. Fusion propulsion enables missions to collect samples from moons, asteroids, and even comets, bringing them back to Earth for analysis. Fusion propulsion supports the construction of space infrastructure, such as habitats, research stations, and refueling depots. These structures can serve as bases for further exploration and as waypoints for longer journeys. The flexibility of fusion propulsion allows for mid-mission adjustments and course corrections. This adaptability is crucial for navigating the unpredictable conditions of deep space. International collaboration on deep space missions becomes more achievable. Fusion propulsion can support large, complex missions involving multiple countries, sharing the benefits and advancements in space exploration. Ultimately, fusion propulsion is a transformative technology for deep space exploration. By providing the speed, efficiency, and power needed for long-duration missions, it opens up new frontiers for humanity to explore and understand our universe. Fusion propulsion opens up numerous scientific research opportunities that were previously beyond our reach. The ability to travel farther and faster allows us to explore the outer planets and their moons in unprecedented detail. Missions to Jupiter's moon Europa can search for signs of life beneath its icy crust. Fusion propulsion enables prolonged missions to drill through the ice and deploy submersibles into its subsurface ocean. Saturn's moon, Enceladus, with its geysers spewing water vapor and organic molecules, becomes a prime target for astrobiology. Fusion-powered spacecraft can carry sophisticated instruments to analyze these plumes in detail. The gas giants themselves, Jupiter and Saturn, can be studied more thoroughly. Fusion propulsion supports missions that can stay in orbit longer, mapping their magnetic fields and atmospheric dynamics.
The ice giants Uranus and Neptune have only been visited once by Voyager 2. Fusion propulsion can enable dedicated missions to these distant planets, studying their atmospheres, rings, and numerous moons.
Deep space missions to the Kuiper Belt can provide insights into the early solar system. Fusion propulsion allows for multiple flybys of these ancient icy bodies, gathering data on their composition and formation history. Exploring the heliopause, the boundary of our solar system, becomes feasible. Fusion-powered missions can study the interaction between solar wind and interstellar space, enhancing our understanding of cosmic radiation and its effects. Interstellar probes equipped with fusion propulsion can investigate the local interstellar medium. These missions can collect data on the composition, temperature, and density of space beyond our solar system. Fusion propulsion supports long-term studies of cosmic phenomena, such as gamma-ray bursts, quasars, and black holes. Probes can be sent to observe these high-energy events from closer vantage points, providing valuable data. Astrobiology research benefits from the ability to reach and study exoplanets. Fusion propulsion can power missions to nearby star systems, enabling the search for habitable worlds and potential extraterrestrial life. Fusion propulsion enhances the study of planetary geology. Missions can carry advanced sensors and rovers to analyze the surface and subsurface structures of planets, moons, and asteroids in detail. Solar research is another beneficiary. Probes can be sent closer to the Sun to study its corona and solar wind, improving our understanding of solar dynamics and space weather impacts on Earth. The search for dark matter and dark energy can be advanced with fusion-powered missions. Probes can be positioned in deep space to observe the universe with minimal interference, gathering data critical to these fundamental mysteries. Fusion propulsion can also facilitate the deployment of large space telescopes far from Earth's light pollution. These telescopes can observe the cosmos with unprecedented clarity, making groundbreaking discoveries in astrophysics. Finally, the ability to carry larger scientific payloads allows for the simultaneous study of multiple scientific questions. Missions can be equipped with diverse instruments to gather comprehensive data, maximizing the scientific return. In essence, fusion propulsion dramatically expands the scope and scale of scientific research, enabling humanity to explore the cosmos more deeply and answer some of the most profound questions about our universe. Fusion propulsion offers a significant reduction in space travel costs by increasing efficiency and reducing the amount of fuel needed for long-duration missions. The high energy density of fusion fuel allows spacecraft to carry less fuel, translating to lower launch costs. With fusion propulsion, spacecraft can achieve higher speeds and shorter travel times, which reduces operational expenses associated with long missions. Faster missions mean less time spent on maintaining life support systems and other onboard operations, further cutting costs. The ability to transport larger payloads with fusion propulsion means fewer launches are required. This reduces the overall cost of missions, as fewer rockets and launches are needed to deliver the necessary equipment and supplies. Maintenance and resupply missions to space stations or lunar bases can be conducted more efficiently and less frequently. The reduced need for frequent resupply missions lowers the operational costs associated with maintaining a continuous human presence in space. Fusion propulsion systems have longer operational lifespans compared to chemical rockets, which reduces the need for frequent replacements and refurbishments. This durability leads to cost savings over the long term. The efficiency of fusion propulsion supports reusable spacecraft designs. Reusable systems significantly lower the cost per mission by spreading the initial investment over multiple trips, similar to the economic benefits seen with reusable rockets. Reducing the weight of spacecraft by carrying less fuel allows for smaller and less expensive launch vehicles. This downsizing of launch systems contributes to overall cost savings for space missions. Fusion propulsion's ability to support in situ resource utilization means that missions can produce fuel and other necessary materials on site, rather than carrying everything from Earth. This capability reduces the payload weight and launch costs. By enabling more frequent and flexible mission planning, fusion propulsion decreases the financial risks associated with delays and missed launch windows. More reliable and timely missions translate to better budget management and cost efficiency. Fusion propulsion can open new commercial opportunities in space, such as asteroid mining and space tourism. These industries can benefit from the reduced costs and increased feasibility of space travel, driving further investment and economic growth. Collaborative international missions can share the costs of development, launch, and operation. Fusion propulsion facilitates these partnerships by making ambitious, large-scale missions more economically viable for all participating nations. The potential for continuous thrust provided by fusion engines allows spacecraft to reach destinations more directly, avoiding complex and costly orbital maneuvers. This direct approach simplifies mission planning and reduces associated expenses. Energy generated by fusion reactors can also be used to power scientific instruments, communication systems, and life support, eliminating the need for additional power sources and reducing the overall mission cost. As fusion propulsion technology matures and scales, the production costs of fusion reactors and fuel are expected to decrease. Economies of scale will make fusion propulsion even more cost-effective over time. Ultimately, fusion propulsion offers a path to more affordable space exploration by improving efficiency, reducing fuel requirements, and enabling reusable systems. These cost savings will make space travel more accessible, fostering a new era of discovery and innovation. Fusion propulsion could significantly boost the space tourism industry by reducing travel times and costs. The ability to reach destinations quickly and efficiently makes space tourism more accessible and appealing to the public. Shorter travel times mean tourists can spend more time enjoying their destination rather than enduring long, arduous journeys. This enhances the overall experience and attractiveness of space travel. The increased payload capacity of fusion-powered spacecraft allows for more amenities and comfort features, making the journey more enjoyable for tourists. Luxurious accommodations and recreational facilities become feasible. Fusion propulsion can support regular and reliable travel schedules, much like commercial airlines. This predictability and frequency make space tourism a more practical and desirable option for potential customers. The cost savings from fusion propulsion can be passed on to tourists, making space travel more affordable. Lower ticket prices will attract a broader range of customers, expanding the market for space tourism. Fusion-powered spacecraft can reach a variety of destinations, from low Earth orbit to the Moon and beyond. Offering diverse and exotic destinations will increase the appeal and variety of space tourism packages. The safety and reliability of fusion propulsion systems will reassure potential tourists. Knowing that the technology is robust and well-tested will build confidence and interest in space travel. Space hotels and resorts can be established with the support of fusion propulsion. These orbital or lunar facilities can offer unique experiences, such as zero-gravity activities and stunning views of Earth and the cosmos. Space tourism can also include educational and scientific elements. Tourists can participate in experiments and learn about space science, adding value to their experience and inspiring future generations of explorers. Fusion propulsion enables longer and more ambitious trips, such as tours of the Moon's surface or flybys of Mars. These extended excursions provide once-in-a-lifetime experiences that will draw in high-paying customers. The development of space tourism infrastructure supported by fusion propulsion will create numerous jobs and stimulate economic growth. This new industry will require skilled workers in various fields, from engineering to hospitality. Fusion propulsion's environmental benefits also appeal to eco-conscious tourists. The clean energy profile of fusion makes space travel more sustainable, attracting those who prioritize environmental responsibility. Innovations driven by the space tourism industry can spill over into other sectors. Advances in materials, life support systems, and propulsion technologies will benefit commercial aviation, healthcare, and other industries. Collaborations between space tourism companies and government space agencies can enhance public interest and investment in space exploration. High-profile space tourism missions can generate excitement and support for broader space initiatives. Ultimately, fusion propulsion can transform space tourism from a niche market into a thriving industry. By making space travel faster, more affordable, and more enjoyable, fusion technology will open the final frontier to millions of people, inspiring awe and curiosity about the universe. Fusion propulsion presents numerous opportunities for private sector involvement, driving innovation and economic growth in the space industry. Companies can invest in the development of fusion propulsion technologies, contributing to advancements and reaping the benefits of early adoption. Private companies can collaborate with government space agencies on fusion propulsion projects, sharing expertise and resources. These partnerships can accelerate the development and deployment of fusion technology. Commercial enterprises can develop fusion-powered spacecraft and offer transportation services for cargo and passengers. This new market could rival traditional aviation, opening up space travel to a wider audience. The private sector can also invest in infrastructure projects such as building spaceports and refueling stations that support fusion-powered missions. These facilities will be essential for sustaining long-term space exploration and commercialization. Fusion propulsion can enable the mining of asteroids and other celestial bodies for valuable resources. Private companies can lead these ventures, extracting minerals and materials that are scarce on Earth. Space tourism is a lucrative opportunity for the private sector. Companies can design and operate luxurious space hotels, offering unique experiences to tourists, supported by the efficient and reliable travel provided by fusion propulsion. The ability to transport large payloads efficiently means that private companies can launch and maintain satellites more cost-effectively. This will boost industries reliant on satellite technology, such as telecommunications and Earth observation. Fusion propulsion supports the development of space-based manufacturing. Companies can produce high-quality materials and products in microgravity, benefiting from the unique conditions of space to create items not possible on Earth. Private sector involvement in fusion propulsion can drive technological innovation. Companies can develop new materials, cooling systems, and safety protocols, contributing to broader technological advancements. Investing in fusion propulsion technology can provide a competitive edge. Companies that lead in this field can set industry standards, attract top talent, and secure lucrative contracts with governments and other enterprises. The insurance and finance sectors can also benefit. As space travel becomes more common, there will be a growing need for insurance policies that cover space missions, as well as financial services that support space industry investments. Educational institutions and private companies can collaborate to train the next generation of engineers and scientists. These partnerships can ensure a steady supply of skilled professionals to support the growing space industry. Fusion propulsion can enhance the viability of space-based solar power. Companies can develop systems to collect solar energy in space and transmit it to Earth, providing a clean and abundant energy source. The entertainment industry can explore new frontiers with fusion propulsion. Filmmakers, game developers, and virtual reality creators can produce content based on real space missions, offering immersive and educational experiences. Ultimately, the private sector's involvement in fusion propulsion will drive the commercialization of space, transforming it into a thriving and dynamic industry. By leveraging fusion technology, companies can unlock new opportunities and contribute to humanity's expansion into the cosmos. Fusion propulsion has the potential to significantly impact the global space economy. By reducing travel costs and increasing efficiency, it can make space exploration more economically viable. Lower costs for launching and maintaining spacecraft mean that more companies can afford to enter the space industry. This increased competition can drive innovation and reduce prices further. The ability to carry larger payloads enables more ambitious projects, such as constructing large-scale space habitats and research stations. These projects can create jobs and stimulate economic activity, both on Earth and in space. Fusion propulsion can also facilitate asteroid mining, which has the potential to unlock vast amounts of valuable resources. This new source of raw materials can boost industries such as construction, manufacturing, and technology. Space tourism can become a major economic sector, attracting significant investment and generating revenue. The increased accessibility of space travel will create demand for new services and infrastructure, further driving economic growth. Fusion-powered missions can support the development of space-based solar power, providing a clean and abundant energy source. This can have a profound impact on the global energy market, reducing reliance on fossil fuels and lowering energy costs. The growth of the space economy can lead to advancements in related industries, such as robotics, artificial intelligence, and materials science. These technologies can improve productivity and efficiency across various sectors. International collaboration on fusion propulsion projects can strengthen economic ties between countries. Shared investments and joint ventures can lead to more stable and prosperous economic relationships. Educational institutions and research organizations can benefit from increased funding and opportunities. As the space economy grows, there will be a greater demand for skilled professionals and cutting-edge research. The expansion of space infrastructure, such as spaceports and refueling stations, can create new markets and opportunities for businesses. Companies can develop and operate these facilities, generating revenue and supporting space missions. Fusion propulsion can enable more frequent and reliable satellite launches, enhancing global communications and data services. This can improve connectivity and support the growth of the digital economy. The space economy can also have a positive impact on environmental sustainability. Fusion propulsion reduces the environmental footprint of space travel, and space-based technologies can help monitor and protect Earth's ecosystems. As more countries and companies invest in space exploration, the global economy can become more diversified and resilient. The space sector can provide new sources of growth and innovation, reducing dependence on traditional industries. The space economy can also inspire future generations of scientists, engineers, and entrepreneurs. As space exploration becomes more prominent, it can motivate young people to pursue careers in STEM fields, driving long-term economic growth. Ultimately, fusion propulsion can transform the global space economy by making space exploration more accessible, affordable, and sustainable. This transformation will unlock new opportunities, drive innovation, and contribute to a more prosperous and interconnected world. NASA and other space agencies play a crucial role in the development and implementation of fusion propulsion. Their expertise and resources are essential for advancing this transformative technology. These agencies conduct fundamental research and development, laying the groundwork for fusion propulsion systems. They leverage decades of experience in aerospace engineering and scientific research. Collaboration between space agencies accelerates progress. Joint missions and shared research initiatives pool resources and expertise, overcoming challenges more efficiently. NASA's leadership in space exploration sets the stage for the adoption of fusion propulsion. Their endorsement and investment in this technology validate its potential and attract additional support from other stakeholders. Space agencies are instrumental in setting safety and regulatory standards for fusion propulsion. They ensure that new technologies meet stringent safety criteria and comply with international treaties. These agencies also provide funding and grants to support research and development. Financial backing from government entities is crucial for the high initial costs associated with developing fusion propulsion systems. Space agencies foster partnerships with private companies and academic institutions. These collaborations bring together diverse perspectives and skills, driving innovation and practical applications of fusion technology. NASA's Artemis program, aiming to return humans to the Moon, could be an early adopter of fusion propulsion. Successful demonstration missions would pave the way for broader use in future space exploration. The European Space Agency, ESA, and its member states are key partners in advancing fusion propulsion. Their collaboration with NASA and other agencies ensures a coordinated and global approach to this technology. The Russian Space Agency, Roscosmos, has a rich history of space achievements and can contribute significantly to fusion propulsion efforts. Their experience and technological capabilities are valuable assets. The China National Space Administration, CNSA, is rapidly advancing its space capabilities. Their involvement in fusion propulsion projects can further accelerate the development and deployment of this technology. Space agencies also play a vital role in public outreach and education. They help communicate the benefits and potential of fusion propulsion to the public, garnering support and inspiring future generations. International space agencies work together on missions that can demonstrate the effectiveness of fusion propulsion. These joint missions showcase the technology's capabilities and build confidence for more ambitious projects. Space agencies are responsible for integrating fusion propulsion into broader space exploration strategies. They align this technology with long-term goals, such as human missions to Mars and beyond. Ultimately, the role of NASA and other space agencies is pivotal in making fusion propulsion a reality. Their leadership, collaboration, and resources will help unlock the full potential of this revolutionary technology, transforming space exploration for future generations. Private companies are becoming increasingly involved in fusion research, driving innovation and investment in this promising technology. Their contributions are crucial for advancing fusion propulsion and making it commercially viable. Companies like SpaceX and Blue Origin are leading the charge in space exploration and could play a significant role in developing fusion propulsion systems. Their focus on reducing costs and improving technology aligns well with the goals of fusion research. Smaller startups and specialized firms are also making significant strides in fusion research. Companies like TAE Technologies and Helion Energy are developing new approaches to achieve practical fusion, pushing the boundaries of what's possible. Private companies bring agility and risk-taking to fusion research. They can pursue bold ideas and innovative solutions that might be too risky or unconventional for government-funded projects. These companies often collaborate with academic institutions and national laboratories, combining resources and expertise to accelerate progress. Such partnerships enhance the quality and speed of research and development. Investment from venture capital and private equity fuels the growth of fusion research companies. Financial backing from the private sector enables sustained development and helps bring fusion technologies closer to commercialization. Private firms also focus on developing practical applications for fusion technology. By creating marketable products and services, they can generate revenue and further invest in research and development. Companies are exploring diverse fusion concepts, from magnetic confinement to inertial confinement fusion. This variety of approaches increases the likelihood of finding a successful and scalable solution. Fusion propulsion developed by private companies can support a range of missions, from satellite deployment to deep space exploration. Their innovations could revolutionize how we travel and operate in space. The involvement of private companies in fusion research encourages competition, driving efficiency and reducing costs. This competitive environment fosters rapid advancements and the adoption of best practices. Private firms often prioritize commercialization timelines, pushing for faster development and deployment. Their focus on market readiness ensures that fusion propulsion systems can be used effectively and profitably. The global reach of private companies means that fusion research benefits from diverse perspectives and international collaboration. This global approach enhances innovation and accelerates technological breakthroughs. Private companies are also playing a role in public education and advocacy for fusion technology. By raising awareness and generating interest, they help build public support and attract additional funding. Corporate investment in fusion research signals confidence in its potential. As more companies commit resources to this field, it validates the technology and attracts further interest from investors and stakeholders. Ultimately, the involvement of private companies in fusion research is vital for achieving practical fusion propulsion. Their innovation, investment, and entrepreneurial spirit will help turn the promise of fusion technology into a reality, transforming space exploration and beyond. Government funding and support are crucial for the advancement of fusion propulsion technology. Significant investments in research and development are needed to overcome the technical challenges associated with fusion. Public funding provides the financial stability required for long-term projects. Unlike private investments, which may be subject to market fluctuations, government support ensures continuous progress. Government grants and subsidies can reduce the financial risk for private companies. By sharing the burden, these funds encourage private sector investment and innovation in fusion research. National laboratories and research institutions play a key role in fusion research. Government funding supports these institutions, providing the resources necessary for groundbreaking scientific discoveries. Collaboration between government agencies and private companies is essential. Joint ventures and public-private partnerships leverage the strengths of both sectors, accelerating the development of fusion propulsion. Regulatory support is also important. Governments can streamline the approval process for fusion research projects, ensuring that regulatory hurdles do not delay progress. International cooperation, facilitated by government agreements, can enhance fusion research. Collaborative projects and shared knowledge across borders can lead to faster and more efficient advancements. Educational programs funded by the government can train the next generation of scientists and engineers. Investing in STEM education ensures a skilled workforce capable of advancing fusion technology. Public funding can support large-scale experimental facilities like ITER. These facilities provide valuable data and experience, essential for developing practical fusion propulsion systems. Government-backed prizes and competitions can stimulate innovation. By offering rewards for specific milestones in fusion research, governments can motivate researchers and companies to push the boundaries of what is possible. Military interest in fusion propulsion can drive funding and research. The potential for defense applications provides an additional incentive for governments to invest in this technology. Tax incentives and credits can encourage private sector investment in fusion research. These financial benefits reduce the cost of research and development, making it more attractive for companies to invest in fusion technology. Government-sponsored public outreach programs can raise awareness about the benefits of fusion propulsion. Educating the public helps build support for funding and policy initiatives related to fusion research. Long-term policy commitments from governments provide stability and confidence for researchers and investors. Clear and consistent support from policymakers ensures that fusion research can proceed without interruption. Ultimately, government funding and support are indispensable for the development of fusion propulsion. By providing financial resources, facilitating collaboration, and fostering innovation, governments can help turn the dream of fusion-powered space travel into reality. Future research directions in fusion propulsion are expansive and ambitious. They encompass advancements in materials science, reactor design, and fuel cycle development. One critical area is the improvement of magnetic confinement systems. Research aims to enhance the efficiency and stability of tokamaks and stellarators, ensuring sustained fusion reactions. Inertial confinement fusion also holds promise. Scientists are exploring ways to optimize laser and ion beam systems to achieve the necessary conditions for fusion in small fuel pellets. Developing advanced superconductors for magnetic coils is another priority. These materials can significantly improve the performance and energy efficiency of fusion reactors. The integration of artificial intelligence and machine learning in reactor control systems is a burgeoning field. AI can optimize the fusion process in real time, adjusting parameters to maintain stability and maximize output. Exploring alternative fusion fuels like helium-3 and boron-11 is vital. These fuels produce fewer neutrons, reducing radiation damage and improving the longevity of reactor components. Materials research focuses on finding and developing materials that can withstand the extreme temperatures and radiation within fusion reactors. Advanced ceramics and metal alloys are key candidates. Innovations in heat management are essential. Efficient cooling systems must be developed to handle the intense heat generated by fusion reactions, ensuring the safety and durability of the reactor. Fuel handling and breeding techniques are another area of focus. Efficient methods for producing and managing deuterium and tritium, as well as breeding tritium from lithium, are critical for sustained operations. Investigating the potential for direct energy conversion is also promising. This involves converting the energy from fusion reactions directly into electricity, bypassing traditional thermal cycles, and increasing overall efficiency. Space-based testing of fusion propulsion systems is a necessary step. Conducting experiments in space environments will provide invaluable data and help refine technologies for practical use. The development of compact fusion reactors is crucial for space applications. These reactors must be small, lightweight, and robust enough to operate reliably in the harsh conditions of space. International collaboration will continue to be a cornerstone of fusion research. Sharing knowledge, resources, and expertise globally accelerates progress and ensures the most effective solutions are found. Public engagement and education are also important. Increasing awareness and understanding of fusion propulsion can build support for ongoing research and funding. Ultimately, future research in fusion propulsion aims to make this technology a practical reality. By addressing the challenges and exploring innovative solutions, scientists and engineers can pave the way for a new era of space exploration. Educating the public about fusion is essential for gaining support and understanding of this transformative technology. Public awareness can drive funding, policy changes, and interest in pursuing careers in fusion research. One effective approach is through comprehensive educational programs in schools and universities. Integrating fusion topics into science curricula can inspire students and foster a new generation of researchers and engineers. Public lectures and workshops hosted by experts can provide in-depth knowledge about fusion. These events can be held in community centers, museums, and educational institutions to reach a broad audience. Media campaigns can highlight the benefits and progress of fusion research. Documentaries, news articles, and social media posts can inform the public about the potential of fusion propulsion and its impact on space exploration. Interactive exhibits in science museums and technology centers can engage visitors. Hands-on displays and simulations can make complex concepts more accessible and exciting for people of all ages. Partnerships with popular science communicators and influencers can amplify the message. Collaborating with well-known figures in science communication can help reach a wider audience and spark interest in fusion technology. Developing online courses and webinars can provide flexible learning opportunities. These resources can cater to different knowledge levels, from basic introductions to advanced technical content. Public demonstrations of fusion technology, such as small-scale experiments and reactor models, can showcase the practical aspects of fusion. Seeing real-world applications can enhance understanding and interest. Creating informative and visually appealing infographics can simplify complex information. These graphics can be shared on social media, in publications, and at educational events to illustrate key points effectively. Government and industry collaboration on public education initiatives can pool resources and expertise. Joint efforts can create more comprehensive and impactful educational programs. Open days and tours of research facilities can provide first-hand experiences. Allowing the public to visit labs and interact with scientists can demystify fusion research and build trust in the technology. Educational outreach programs targeting underrepresented communities can ensure inclusivity. Providing access to fusion education for all demographics fosters a diverse and equitable future workforce. Developing mobile apps and interactive websites can provide ongoing engagement. These platforms can offer updates on fusion research, educational games, and virtual tours of fusion facilities. Involving the public in citizen science projects related to fusion can create a sense of participation and investment. These projects can allow people to contribute to real research efforts and see the impact of their involvement. Ultimately, educating the public about fusion is about building a foundation of knowledge and support. By making fusion concepts accessible and exciting, we can cultivate a society that values and advances this critical technology for the future of space exploration and energy. The role of media and influencers in promoting fusion technology is crucial. Media outlets can highlight the latest advancements and successes in fusion research, helping to inform and educate the public. Influencers can leverage their platforms to share exciting news about fusion propulsion, making the topic accessible and engaging for their followers. Their reach can spark widespread interest and curiosity. Documentaries and educational programs about fusion can provide in-depth explanations and showcase the potential benefits of this technology. These formats allow for a comprehensive understanding of fusion's impact. Social media campaigns can create buzz around fusion breakthroughs, using hashtags and viral content to spread the message quickly and widely. Engaging visuals and infographics can make complex concepts easier to grasp. Podcasts featuring interviews with fusion experts can delve into the science and significance of fusion propulsion, reaching audiences who prefer audio content. These discussions can demystify the technology and its applications. YouTube channels dedicated to science and technology can produce detailed videos about fusion, demonstrating experiments and explaining theoretical concepts. Visual content helps in making the science behind fusion more tangible. Influencers in the STEM community can collaborate with fusion researchers to create content that bridges the gap between the scientific community and the general public. These partnerships can enhance credibility and reach. Traditional news outlets play a significant role in reporting on major milestones in fusion research. Comprehensive articles and news segments can provide context and highlight the importance of these developments. Bloggers and science writers can produce detailed articles that explore various aspects of fusion propulsion, from its history to its future potential. Written content can cater to those who prefer to read and reflect on information. Media coverage of fusion technology can influence public policy by raising awareness among policymakers and the general public. Well-informed citizens can advocate for increased funding and support for fusion research. Educational influencers, such as teachers and lecturers, can incorporate fusion topics into their curricula and lectures. By educating students, they lay the foundation for future generations of scientists and engineers. Influencers can organize and promote events such as webinars, live Q&A sessions, and virtual tours of fusion research facilities. These interactive formats engage audiences directly and allow for real-time learning and discussion. Media platforms can host debates and discussions about the challenges and opportunities of fusion propulsion, providing a forum for different perspectives and fostering a deeper understanding of the topic. Books and publications by respected authors and scientists can provide authoritative insights into fusion technology. These works can serve as valuable resources for anyone looking to understand the science and implications of fusion. Ultimately, the media and influencers have the power to shape public perception and understanding of fusion technology. Their efforts can help build excitement, support, and momentum for the continued development and implementation of fusion propulsion. The impact of fusion propulsion on STEM education is profound. It can inspire a new generation of students to pursue careers in science, technology, engineering, and mathematics. Fusion propulsion represents a cutting-edge technology that combines principles from multiple STEM fields, offering a rich context for interdisciplinary learning and exploration. Integrating fusion propulsion topics into school curricula can make learning more engaging. Real-world applications of physics, chemistry, and engineering can help students see the relevance of their studies. Hands-on projects and experiments related to fusion can stimulate interest and curiosity. Building simple models or simulations of fusion reactors can provide practical experience and deepen understanding. Fusion propulsion can be used as a case study in advanced courses. Topics such as plasma physics, materials science, and nuclear engineering can be explored in greater depth. STEM clubs and after-school programs can focus on fusion propulsion. These extracurricular activities can provide additional opportunities for students to engage with the subject and develop their skills. Competitions and challenges centered around fusion technology can motivate students to innovate. These events encourage problem-solving, teamwork, and creativity, essential skills for future scientists and engineers. University programs can offer specialized courses in fusion science and engineering. These programs can prepare students for careers in the growing field of fusion research and technology. Internships and partnerships with fusion research labs can provide valuable real-world experience. Students can work alongside professionals, gaining insights and practical knowledge. Educational resources such as textbooks, online courses, and multimedia content can be developed to support learning about fusion propulsion. These materials can be tailored to different educational levels and learning styles. Teachers and educators can receive professional development and training on fusion topics. Equipped with up-to-date knowledge, they can more effectively teach and inspire their students. Public outreach programs can include workshops and seminars on fusion propulsion. These events can engage not only students but also their families and the broader community. Fusion propulsion can also be a topic for science fairs and research projects. Students can investigate various aspects of fusion technology, from theoretical principles to potential applications. Educational institutions can collaborate with fusion research organizations to stay at the forefront of developments in the field. These partnerships can ensure that educational content remains current and relevant. By integrating fusion propulsion into STEM education, we can cultivate a workforce capable of advancing this transformative technology. The excitement and innovation generated by fusion research can drive educational excellence and inspire the next generation of pioneers. In this video, we explored the incredible potential of fusion propulsion to revolutionize space travel. We started by examining the basic principles of nuclear fusion, understanding how combining light atomic nuclei releases vast amounts of energy, far exceeding what current chemical and nuclear fission technologies can provide. We then compared fusion propulsion with existing technologies, highlighting its superior efficiency, safety, and minimal environmental impact. Fusion's high specific impulse and continuous thrust capabilities make it a game-changer for long-duration missions to distant destinations such as Mars and beyond. The discussion moved to the current state of fusion research, where we covered major players and the exciting progress being made in both public and private sectors. We learned about the various designs being explored, including tokamaks, stellarators, and inertial confinement fusion, each with its unique approach and challenges. We also addressed the importance of government funding and international collaboration, emphasizing how these efforts are critical to overcoming the technological hurdles and making fusion propulsion a practical reality. The role of NASA and other space agencies in pioneering this research cannot be overstated. Safety and efficiency are paramount, and we delved into the advanced materials and shielding techniques required to protect both the spacecraft and its crew from the intense conditions of fusion reactions. Handling fusion fuels safely, especially tritium and deuterium, is another crucial aspect we covered. We discussed how fusion propulsion could dramatically reduce travel times, making human missions to Mars not just feasible but significantly more efficient and safe. The potential for lunar bases and other space infrastructure was also highlighted, showcasing how fusion could support sustainable and long-term human presence in space. Exploring the role of media and influencers, we recognize their power in educating the public and generating excitement around fusion technology. Accurate information and engaging content can drive public support and inspire future generations to pursue STEM careers. The economic implications are vast, with fusion propulsion likely to lower the costs of space travel and open up new commercial opportunities, from space tourism to asteroid mining. The private sector's involvement is crucial in driving innovation and bringing these technologies to market. In the realm of STEM education, fusion propulsion serves as a powerful tool to inspire students and foster a new generation of scientists and engineers. Integrating fusion topics into curricula and providing hands-on learning experiences can ignite a passion for discovery and innovation. If you enjoyed this video, please like and subscribe to our channel. Your support helps us create more content like this and keeps you updated on the latest advancements in space technology. Don't forget to check out the rest of our videos for more fascinating insights into the future of space exploration. Thank you for watching.